a toggle on the top.
Okay.
Okay. Please let me know when is a good time to start. All right. One up. All right, good morning, everyone. Thank you all for being here. My name is Luis Ubiera. I'm the lead firmware engineer at Croxel, and I'm here to talk about application development with TDD, getting started. So test-driven development, it's a discipline that has been growing more popular over the years, but still we believe at Croxel that there is not enough adoption or there is not enough awareness of the people wanting to make use of it, understand their benefits, or they just think of it as like a concept that works in theory, but they're not sure if it works in practice. So here I am to talk about a little bit more how to get started, kind of like prove that it somewhat works, and how to apply it in Zephyr. Because on top of this, you have the Zephyr RTOS, which is very powerful, but some people might find it a little bit intimidating. So if you add TDD on top of that, they may not be able to figure out on their own what it's all about with all this complexity. So hopefully we'll break all of those down. I'll give you a good head start on applying TDD for firmware applications using Zephyr. So the agenda today will be pretty short. Hopefully we'll have time to do a live demo. First an intro, then we go over, skimming over the basics of test-driven development. We kind of break it down what TDD in Zephyr looks like. We give a specific detail of just a couple tips of how to fake dependencies in Zephyr, specifically using when you deal with device tree nodes and complex subsystems. Finally, we do a live demo. Hopefully, we'll get something useful out of it, and we will have time for questions. So intro. I studied electrical engineering, but ever since I got in the field, I gravitated towards software. So that is what I found to be my passion, firmware development, very close to the hardware, essentially making software for things that aren't computers, electronics, right? So I've been doing that ever since I got out of college. I am the lead firmware engineer right now, as I mentioned many times right now. I only have 7 years of experience. I found a lot of learning and catching up with the new technologies are always coming up. So I'm based in Melbourne, Florida. A lot of people ask, is this in Australia? It is not. It's in Florida. It's the Space Coast. That super nice image that you see on the right is one of the perks in living in the Space Coast, because every other week you have a rocket launch. So you could be getting groceries and you happen to see a Falcon 9 just flying, deploying satellites or something. It's really nice. And the scenery there, it has a lot of engineering vibes, so it's a really nice place to be. You should visit it sometime, not related to this presentation. As I mentioned, I have passion for technology, electronics, and IoT. My first Zephyr contribution, so I'm a Zephyr contributor. Oh, I don't have my tag here that says that I'm a contributor, but I am. My first contribution was in 2021. When I'm not doing engineering, coding, or anything else, I am into fitness and sports. I recently started a blog called embeddedtales.blog, and I have one series that I'm currently working on that's called Zephyr, the Linux for MCUs. Make sure to check it out if you're interested. And nevertheless, I'm a first-time speaker at Embedded Open Source Summit, so please bear with me. Let's talk a little bit about Croxel. What's Croxel? So we are a team of engineers, passionate engineers that do firmware, hardware, and product level design. We provide services. We do consulting. Specifically speaking, one of our strengths is Zephyr RTOS. So we do firmware development. We're big into Zephyr. Most of our applications that we develop for customers are based on Zephyr. We offer different services from like product development end to end. People come up with an idea and they say, I want to go to production. We pull together we allocate a team of engineers and we develop the solution in terms of hardware and firmware as well. We also are up for rapid prototyping. So you want to show up something to leverage like business interest or value. We also are able to do that. Or we can also team up with your team of engineers. You have a team of engineers that you don't feel comfortable with the tools that they're using, or you think you need more. We are able to integrate with your team, do agile, and couple into what your dynamics of their company do. And obviously, we are active contributors in the Zephyr project, and we hope to only keep increasing that contributions over time. All right. I'm sorry. Basics of test-driven development. So it's hard to define what TDD is, and a lot of people have done amazing work to already do that. So I'm just going to mention a few things for somebody who's not really in context of what it is, you can get a glance of what this is, and then just hopefully research yourself. There are books already there that you can check up. Fundamentals for this, essentially, is like TDD comes from extreme programming. It's totally the opposite of typical waterfall development, where you develop the code base first, and then you attempt to test it to get the bugs out of it. It focuses on incremental development, so small portions of increment, one at a time, and that's the way you build up all the whole progress. And finally, one thing that I believe is really important is that test-driven development embraces the fact that bugs are inevitable. Let's face it, it's not a bad thing. You shouldn't be ashamed of your bugs. You should embrace them, and as such, you need to do something about it. So TDD actually faces that by developing a methodology to systematically catch those bugs, most of the bugs that you usually come up with, because we're humans, we make mistakes. And finally, an interesting aspect is that TDD relies on capturing and passing unit tests as means to develop the application. So you write a test, you describe what the expectation is, you make the test pass, and you come up with the set of tests and expectations. Then you lock in the behavior of your module or your software application so that it passes all the tests. This is an image I borrowed from James Scramning. I personally consider that he is one of the guys who actually brought this TDD into embedded. Essentially, kind of like the life cycle of a bug. When do we usually inject a bug, and when do we know that we have a problem, and when do we fix it? So in a regular development cycle, meaning you develop everything first and you start testing things, the time at which you inject a bug is obviously during development. You have like this set of requirements that you're putting all together this code that seems to be working, right? You run it until you believe, hey, everything seems to be all right? Then there's we have their TD is the time for you to discover the bug. The time that you know you have a problem. Hey, something's not right here, and everything was working, but now it appears we missed something. And then we have the T-find, which is the time to find what the root cause of the bug is, and obviously the time for fixing it. The time usually between the injection and the discovery of the bug could be days, good if you're lucky, weeks, or even months. Or I would even put it in perspective. You could release these bugs. You wouldn't be able to react on it because it's already deployed. You have customers that are suffering from it. The time to find it, it's always I guess exponentially, the more time you take to find the bug, the more you're probably going to take to actually find what the root cause is, because you have so many things pulled together. Your mind might not be fresh on what the code that you touched on was doing, and so forth. And the time to fix it, I guess, depends on the root cause. But I guess the hardest part of the bugs, typically, in my limited experience, is that once you find what the root cause is, it's easy to fix it. But it's really hard to really find what it is. Usually, maybe represent or exhibit it in different manners that you may suspect other things might be going on. OK, so we are familiar with that one. Let's see this one. Bugs in a TDD development cycle. Usually, and obviously there are exceptions, but in general, what TDD focuses on is, as we're developing the code, we're testing it. We develop a small portion of the code, And we right now make sure that our expectations are met. So generally speaking, when you inject a bug because you didn't do something that you didn't do what you thought you wanted to do, the test will tell you. It will fail, and it will tell you a description of, hey, this expectation wasn't met. So as such, the time between injecting a bug and discovery could be minutes, seconds, minutes. I don't know. How long, depending on how long you take to write the test and to exercise that cycle. And the time to find it, it's the root cause. It's also very short because everything before the last change you made was passing. So you made this last change, this new change, things are broken. What could have caused it? The last thing you put in. It's much easier to find things. And obviously to fix it because you really know, oh, this is not what I thought, and you just immediately correct it. So I was talking about a cycle, what this cycle is about. So essentially with TDD, you need to get comfortable with tests failing. It's just the first thing. People don't like when their code doesn't compile or something goes wrong. You need to be comfortable with that as long as it is what you are expecting, right? So with the TDD cycle, essentially it's about writing a test, writing a failing test, making it pass, and then refactoring. And then essentially kind of like you start with a list of requirements. And I'm here not talking about like all the application. You should obviously decompose your application in individual modules that have a single responsibility and a purpose. And those modules that you have broken down your application into have some sort of requirements, right? Then you kind of transfer what those high-level requirements of your module do. You transfer those to a list of tests. Okay, so this this requirement should mean this and that. And you then put in your tests one at a time, and you apply the cycle of fail, pass, refactor. Red, green, refactor. So essentially, you first might make the test. Obviously, you haven't written any code. You run it. It fails, obviously. You make the minimal change that you can so you can make the test pass, and then you refactor the code. And then you put more tests, and so on. And essentially, each of those tests contribute to locking in this behavior that we want on the module. And obviously, it's possible because this is agile. So as you're writing the tests, don't try to spend too much time to get all the tests at once before starting to iterate. It's fine if you don't have everything figured out. Some of those things might come along the way. You may realize as you're running the test, oh, I realized that I need this additional test, and so forth. So keep that in mind. I'll give you an example here, just in pragmatic terms. What if we're talking about a software module that goes embedded in a wearable that should detect motion? So I'm here putting a name, motion detection engine. So the ability and the purpose for this module would be to detect is the device or is the wearable moving? Is it idle, or do we not know? So as a requirement, that's the first thing. The second one would be upon initialization, the motion state is unknown. We don't know what's going on, so we're detecting it. Idle means that no motion has occurred in the last 5 seconds. So if you have your device idle for 5 seconds, after those 5 seconds, it'll tell you it's idle. Movement means, and this is really arbitrary, please don't criticize with this module. Let's just assume that those are the requirements. Movement means that detecting at least 2 meters per square second of acceleration on any axis for at least 1 second. Let's assume that that's the case. And every time we change the state of the motion state, we get a callback, or we get a trigger an event so that users know that that's the case. This is an attempt to transfer those requirements in tests, just pretty similar, but just in a way that now you're thinking about code. So number one, I put that initializing the module starts the motion detection engine. So you just initialize it and you start detecting it. The initial state is unknown. It's just pretty much a transfer from the requirement. You have a callback, as I mentioned, that you trigger on a state change. How do you bridge that callback to notify the users? Okay, that's up to your application design, whatever it's trying to do. For instance, if it's BLE or something else. The transition to idle state if no motion in 5 seconds. So essentially the system transfers to goes to into idle state, no motion. You go into movement state if motion is sustained for 1 second. And once entered in motion state, you stay in that state for 5 seconds. So that's kind of like the premise. So you have like a cool down period in which you think you're in movement state. You probably are not experiencing movement, but you'll stay there as long as you have there. Sustained motion while in movement state extends the motion state. So if you experience motion, 3 seconds later you just move it again, you should like delay the transition to idle state. This is all arbitrary, but just trying to depict an example of what this should look like. We'll come back to this later on the presentation. Just like after, okay, so we understand what the cycle is. We just saw an example. Let's talk about dependencies. Here in embedded, dependencies are really important. Sometimes those dependencies are hardware, pieces of hardware, or so like software stacks and whatnot. So to fake dependencies, generally speaking, you have like a unit under test that you rely on some dependencies to do the functionality you want. And essentially, you fake those dependencies by putting a test double. And essentially, what a test double does is mocking or faking the behavior of what your dependencies should be doing so that you can test it without those dependencies. And there are many types of test doubles. In the picture, let me just say, like, the test double actually sets and manages the expectation and returns the parameters. If we think of an API, essentially, you just validate what the arguments you're receiving are those expected, and you just return a response. And those could be of any type. So you could have like a dummy test double, a stub, or a mock. The difference between these three is how fancy or how specific you want to make the test double. The dummy just like, it's there to fake, it's like, it's there, but don't expect too much emulation of the behavior. It doesn't do much. Stub, you start to like putting some logic on this test double, but it doesn't do all of the things. It doesn't validate, for instance, the order at which you call that API compared to other ones. And essentially kind of like it's a halfway. You have some meat on this test double that you want some logic to be emulated on. And finally, the mock is the most refined one, in which you not only validate what the parameters are, the return values, but you also make sure that the number of times you've called this API, the order compared to the other APIs in this module, are the way that they should be. So you can set all these expectations. So dummy, stub, mock, depending on what your needs are, you could use any of these, or just solely one of them, depending. And you may implement these test doubles manually, or you could use a framework to do that. So there are frameworks right now that you can leverage to, hey, I want to mock all of these API, or I want to fake this dependency, and there are frameworks that do that, especially for instance, like CMOC, CPPU test, and FFF, which I think it's a function framework. Fake function framework, I'm sorry, yeah. So what are we doing this for? What are the benefits? So in a high-level perspective, if somebody just comes in without any context, why would I want TDD? Well, this is why you care. Software development, you can do software development without doing hardware. So like business logic, things that don't really rely on the hardware, you don't need to wait for that to be available for starting that development. You can start that without it. You can catch bugs easier and faster, as I kind of like described before. The definition of done is clear. This is an important point because a lot of times developers, and I'm included myself in that, I've been there before, you're trying to implement a module or an application that does something, and you have the sensation that, okay, once it starts working, if you're doing like develop first, test later, you have the sensation this is working, but I'm not confident that I'm done. So you start to come up with like things that you think should be there, so you add a thing here and there and there and there, so that the things that you're coming up with in the moment are kind of like addressed. But no one's keeping track of that, and sometimes those changes are not exhibited to the surface. So who makes sure that those things don't have bugs, right? The definition of done here is clear, because if all the tests pass and you don't have any more tests to write, well, it seems like your application is done. The definition is done. It's clear. So as such, you improve the predictability of the development cycle. The code base feels less fragile. I'm sure you guys have run into this scenario of, hey, this production code is there, but don't change it too much. and people are afraid to refactor things because, this is working. Let's not question this. Otherwise, it's your fault because you changed it and you broke it. If you have the test suite or the test harness installed and you're running the test all the time, it's easy to know during a refactoring, hey, something broke, and you catch it right away. So the feeling of the code being fragile is not there. You have this safety net to verify that the code does what you think it does. And as such, it improves the overall code quality. Sometimes I run into this scenario where I find a modular functionality that I think it's hard to test. Hey, I don't think this is testable. That is an easy symptom. That is a first symptom that maybe you're not structuring your application well enough. You should rethink the way you're putting the things together so that you can make your code testable. TDD in Zephyr. So apply to Zephyr. What frameworks do we have available? So this is not an exhaustive list, and I see some people in the crowd that are dedicated to testing. Please bear with me if something is not there. C-test is generally used for the Zephyr test framework. FFF is used for mocking. You can use that for mocking. Twister as the test runner, among other things. You also have a radio simulator, for instance, for Bluetooth, which is BabbleSim. And now you have PyTest, which is, among other things, you can use for integration tests on top of Twister. This is very subjective, but what I think are the pros and not the cons, but the complexities adjacent to Zephyr. The pros is that Zephyr has a lot of extensive board support. So you can simulate, you can run the tests, not only on a host environment, but also you can running on different architectures and see how the test responds, right? Zephyr inherently comes with abstractions and generalized APIs that do promote a good structuring for you to test your application. So that is a nice thing to build upon. And that we have testing frameworks available and supported by Zephyr. It's not something that you're trying to port and try to make it work with Zephyr. Zephyr offers for those. Not cons, but complexities. People might find intimidating dealing with device tree. It's like, hey, if they're struggling to set a node in the device tree and make things work, how are you going to fake it? It's like it's another step a little bit beyond. And sometimes the subsystems in Zephyr, it's like they're trying to accomplish a lot of things, or like they're a very complex problem. So you might find issues trying to mock all those things. Specifically, additional on top of that, just like the kconfig dependencies, some people may struggle with, hey, how do you enable or disable, how do I control this behavior? You need to have this control to control what's in, what's out, what's fake, what's not. Okay, so when you're trying to fake dependencies in Zephyr, oh, hold on, just real quick. Okay, yeah. I just want to make sure that was there. When you're trying to make your fake dependencies in Zephyr, for instance, subsystems, you may have alternatives. So the first one is that you use an existing Zephyr emulator. Zephyr provides some emulators for you to test with and you to fake the behavior of those modules or those subsystems. So if you think that you can leverage that, don't reinvent the wheel. If it works for you, don't just because you want to have control. It's like, hey, if it's there, make sure you understand it and use it if possible. The alternative is to implement your own test double. And just like here are a few bullet points of how to do that in general terms. So if you're familiar with the build concept, essentially you build individual modules into object files, and then you have this link time step in which all the object files are correlated. So if you have like include directives in the modules, that's where those things are resolved. So the approach that I recommend when implementing a test double is to go for link time substitution, essentially. And how do you do that? Essentially, you make the object file or the module that you're trying to fake, you don't include it in the build. And that means disabling using kconfigs. For instance, if you're trying to implement like a module that you don't want, you just don't, and implement it yourself. Just implement a test double, link it, and then you can add a minimal test double and implement the used APIs, essentially. Sometimes also like the subsystems may have a ton of APIs. You don't need to fake all of them. You just fake the ones that you expect to use. And That's how you actually fake those dependencies, and one of the approaches for going about it. When you are faking a device tree node, same thing. There are some emulators. I don't have right now the list with me, but if you search through the tree, you will find that there are some. I think you have a SPY emulator, UART emulator, among other things. So make sure to check those out to see if it works for you. If for any reason you decide that you don't, or that just isn't there or isn't suited for your purpose, you can come up with a test double. For lack of a better name, I called it device tree node test double. And when you are implementing a DT node test double, you just add a device tree node with a compatible property that matches the faked module driver that you're trying to fake. So essentially, kind of you implement the property, the fake module as a driver. You make the fake the compatible property. You link it on the device tree node for instance, as an overlay. And it's important that in your module, in the device tree, you rely on, for instance, node labels, that it's easy to fake. So essentially, kind of if for the motion detection, you say, hey, I want to see just give me the accelerometer, for instance. Give the motion accelerometer. And then that could be linked to an I2C device, a device that's on the I2C bus or in SPY, or it could be a faked accelerometer. Obviously, you check expectations, provide return parameters, whatnot. OK. So at this part of the presentation, what I would like to show you guys is what is that in terms of, so in a pragmatic way, what does that mean? So I'll show you what a test suite is, how to define test cases, and we go one by one just to get the feel for what this iteration cycle looks like. Hopefully you can see my screen. Anybody? OK. Yeah. Yeah, so right now here I put together what module test motion detection. And here we have the test suite defined for this. The name of the suite. We have a single test case, for instance, just for verification that the hard disk is installed. And here we have a few things to consider. Every time you execute a test, you have a function that executes before you execute the test, and then you execute another function. Sometimes you call that setup, execution, and tear down. But the nomenclature may vary. But in essence, that is what it does. And here I have, in a comment, just a list of tests that we had written on the slides before. So let's do a couple things just to get the feel for what that looks like. I have here. Let me see if I have it over here. There you go. So I'm going to build this command. You could use Twister for this. I'm just going to use what's built just to get the instant feedback on the screen. But you could use Twister to execute simultaneously many test suites in case that is something you're looking into. So just build it as an application. So essentially, you have the module, but you're using the module on a separate application, not the one you're trying to develop. And essentially, you just run it, and the result looks like this. Essentially, you have a single test that passed, and obviously this test passed because our expectation was that it was true, and we set it to true. That's just to validate that the hard disk is installed. Everything is in place. Now we can work on top of this. So let's find let's say that we do this test. And I'll probably just copy paste this a few times. Let's say test init OK. Let me start simple. Let's say that you have, the expectation is to have something like this. OK, so this is very simple. The goal here is that we have an API, an initialization API, and that it succeeds, meaning that it returns 0. We just wrote it. And obviously, it doesn't work because we haven't done anything with it. So the steps here is that first, you detect that you have an implicit declaration. Obviously, we don't have it defined in our header file. And I'm just going to go over here. As you can see, this is an empty file, motion detection. So I'm just going to do then we iterate once again. Okay, let's see. Now it fails, but not because we have an implicit declaration, but because we don't have a definition for this. It's what we expect. If it failed for any other reason, stop, figure out what is going on. In this case, it's what we expect. So right now, I'm just going to do the slightest thing to make this thing pass right now. So my subsystem is defined over here. And I'm just going to do this. New line. And it passes. So, okay, but the code is not doing anything, right? But we have verified that we've installed this new API, that it's there and it's doing nothing, but that's the job of what we will do next, right? So, for instance, what if we say, let's do... So just one thing I wanted to mention as I'm going through this. Obviously, as you're developing the test, you should have an idea of what the behavior should be. So this is not a replacement for sound design. So you should have kind of the idea of what you wanted to do. And as you're going through the test, you force the test to go in that direction. So it's not about not thinking what should be doing, but actually kind of having an idea. I hope that is clear. And so let me just go on with detection, test suite. And let's say that initial state. We can do, so which test are we going to do? We're going to do callback gets triggered on a state change, let's say. So essentially, we initialize once again. We can verify that this is OK. And then let's assume that we have expectation is that we have, let's say, have an enum with a new state. And this could be so essentially you just keep track of this. Let's say that okay, so every time we get that callback, we'll get that little increment. So after we call this, we should verify that state change it's equal to 1. And that is our expectation. This doesn't fail, and it doesn't fail because we don't have the enum type defined. That is expected. So right now what we do essentially is just define let's just put something here, invalid, and now we just try it again. And this time it did work. It did, work in meaning as in it built and it ran, but it failed. And the reason why it failed is obviously because the motion state called is not 1, it's 0. It's not doing, it isn't doing anything. So we just do the lightest thing to change this behavior. And for instance, essentially kind of we're relying on this callback, right? But nobody's calling it. So I guess one way to go about this would be to say motion detection, for instance, and we just pass on this function. Let's say that we have this API that we called before. We run it again. We made a small change. We verify that now this API obviously is not declared. So we declare it. And for what I'm going to do is I'm going to define let's say that this is the handler. Okay. Still, we fail because we don't have this API defined. So, sorry. And then we can simply go in here. So I can just run it again, and now we don't know what this type is, and it's because we haven't included motion detection. Now included. Hold on. Oh, I mistyped it. So this type of errors just happen all the time. And this time, as you can see, as I'm making these mistakes, I'm figuring them out quickly, right alongside, as I'm writing the test. So it now runs again, still fails. And now let's make the slightest change to make it work now that we have all this in place. So let's say that we have this internal that we have in here. And let's say when we initialize, let's say that we just call it. We just receive the parameter. Let's say that it's this, just for sake of this. And it passes. This time passes, and the code doesn't look to be complete, but it's written by the test. As by the number of tests that we have right now, it's passing them all. So the idea is to then add another thing and another thing on top of this, and we can continue going on. I would like to have a few minutes just to have questions. So what I'm going to do, I think which branch and I am. So I prepare this ahead of time. I have like a set of like what does it look like if you just work on it for a while. I'm just going to hold on. Okay, it doesn't matter. I'm going to check out to demo TDD to rebased. Let's check what's going on here with Git. Oh. Okay. Let me close this, don't save it. So after a while, if you've been practicing TDD, this is what the test cases should look like. Hopefully you guys can see it. The time I did it was motion OK. We initialized it, was OK. And we had another test case for when enabled. So if you enable it while enabled, you essentially kind of like you have a response that, hey, you already enabled it. That's one thing that, as we came across, I put it in place just to make sure. If you initialize it, starts the engine. So now there's an API. I came up with an API to say, hey, is this enabled? If it's disabled before initializing, you should see the state. I'm sorry, if it's not enabled, you should see that the state is disabled, and so forth. So this code is available for you guys to check out on public repo that I'll redirect you to. But essentially, kind of like here is an interesting case where you have make sure that the accelerometer, for instance, pulls once a second. So in this case, I came up with a test double for the accelerometer, implementing what I described. So you have this driver. that you initialize as such. It complies with the sensor driver APIs. In this case, I'm relying on sample fetch and channel get. And it's just emulating the behavior of it. So as, sorry, going back to this. Okay, yeah, so as we're going back to this, you can make sure that the accelerometer has been called once with channel sample fetch and channel get, and so forth, twice, 3 times, and so forth. Okay, so the good thing about this is that simultaneously, as essentially once you have like the test written and everything seems to be working, everything passes and you think you're done, it's easy for you to test it. For instance, the motion detection, just to validating on hardware. This is what the API looks like if you've finished and you've gone through all the tests. And I put together a sample. So essentially, the sample is very simple. You initialize, you add a listener, and you initialize motion detection. And it's just going to print out if the state changed. Let me see if I can quickly just run through that. I think we're running out of time, so let's see how fast can I do this. I'm going to be using a board that has that is battery powered and has an accelerometer on it. I'm going to use Bluetooth to see the console on it, so I can check it out. So we're pulling it. Okay, so it's flashed. I'm going to use Bluetooth to see what's going on here. Hopefully, okay, there you go. So the messages that are here are on this battery-powered device with the stuff that the module we developed with test-driven development. As you can see, it's now set to movement. Let me see if it's now idle. Move it, movement. Idle again, I move it, I keep moving it, and it should not transition to idle state, as our expectations are. Seems to be working. So TDD allows you to make sure what you think you're doing, it's happening. Now the question, is that the right thing? That's another question. But at least from what you think you're doing, the code will be doing what you think you're doing. So it allows you to rethink what should the code then be doing, so you focus your attention on that. Yeah, that's all for now. I'll redirect the repo. It's there right there. You can see it, and it's public. You can check out the sample with all the test cases captured in detail, plus the sample. Thanks for your time. I'll have some questions briefly. Any questions? Okay, yeah, I was hoping you weren't overwhelmed by my presentation. There was a lot of stuff. Sorry. Okay, so I can still hear you.
Also, that your experience to test, be able to get code coverage, test code has to be driven out of main and into, if you like, libraries.
So I'm sorry, could you repeat the question?
Yeah, you can't actually test code in main.c, if you like.
So, okay, yeah, so unit testing focuses about units, right?
Yeah.
It's about module and a thing. I think that doesn't exclude other types of testing like integration testing.
Yeah.
So essentially, this allows you to build the modules that do like the purpose and like dedicate, for instance, motion detection. You wouldn't be dealing about accelerometer or I2C transfers or anything like that. So that allows you to, what are you going to do with that information, and maybe some other types of like testing, testing integration testing will be better for that.
Okay.
Yeah.
Thank you.
It's great for libraries and modules and subsystems, like have a dedicated purpose.
Okay. Thanks.
What? Oh, okay.
Thanks. I was wondering with the test stub for the accelerometer, you had a test that made sure that it worked every second. Do you run a thread in your test module that does that?
Yes, let me show you that. Yeah, so as a response to that test case that was captured, in this module I define a thread. And essentially this thread, the simplest thing I did was just to insert a 1 second delay, and every time you just sample it, and I just put it in a history buffer, just keeps track of what are the latest samples. In this case, ended up being 5 samples. So essentially, that's all we care about, right? Is there motion in the last 5 samples or not? And essentially, that's how it came up to be. Yeah, it's unfortunate that I didn't have time to go over it. I wanted it, but still, the code is there. You can check it out as the link I shared. Any other questions? Yeah.
Thank you very much. Oh, there's one more. Okay, and then I think this is it. Okay.
Last question.
Does this approach work with drivers that interact with memory? For example, if my driver is reading or writing memory, will I be able to write a table for the memory? And
Yes, it works. Yes, and I believe later today there will be a presentation about that. I'm not sure. Yes, it does work. There are ways you can fake memory map devices, so it is possible.
Okay. Well, thank you very much.
All right, thanks
And-
everyone. Appreciate your time. Thank you. Thank you. Oh, let me turn this off.
Walk you through the scenario. Thanks.
Hey there, Mike. This is Ethan with E3 Webcasting. Just wanted to test your mic real quick and make sure everything's coming through loud and clear.
Yeah, how's it going, Ethan? Can you hear me?
Yes. Looking great.
Marvelous.
So your video is great. We got your slides, and audio sounds good too.
Okay. And this is it 11:55 to, or sorry, 9:55 to 10:25? Is that the time?
Yes. Yep. Perfect. So just
Okay.
got a couple minutes here. Kate is going to kind of introduce you and then give you the go ahead
Oh, nice.
once it's time. So we'll mute ourselves here, and you'll hear the introduction in just a few.
Should I expect questions?
I would say yes.
Okay. All right. Thanks.
Yep.
If there's questions that are coming in from the room, Mike, I'll relay them for you. And
Okay. Sounds good.
we should be good. Okay. And I'll
All
try
right,
to
thank
keep an eye on the chat as well.
Okay.
Hey, all, welcome. I think we're probably getting started right now. Thumbs up from the back. Thumbs up. Okay, cool. I'd like to introduce Mike, who is going to be talking about Build Before Installing. This is happening live virtually. And if you've got people in the room, if you've got questions, just raise your hand and I'll bring you the mic. Those who are online and watching remotely, feel free to use the Discord channel if you've got that access to the ZDS-2024 if you've got any questions, and I'll also relay them on. I think there's supposed to be a chat, but we're trying to figure out how to make that happen. So we will hopefully make some progress, and so anyone who's working remotely, if they want to ask questions, we've got a few connections. And with that, I will turn it over to Mike. Thanks, Mike, for doing this.
Absolutely. Thank you, Kate. I really appreciate the opportunity to speak here and the wonderful introduction. It's a great conference. I've been there the last 2 years. I couldn't make it this year, but I'm happy to participate virtually and to talk about the concept of how can we get people building Zephyr code faster. So one of the worst things about embedded development, I think, is managing tool chains and managing build environments. There's a long, sordid history of it, and things are so much better now. But we still find that even with the strides that Zephyr has made in kind of encompassing an ecosystem, getting that first local install up and ready to build can be challenging for a new user. And that might not be the best first introduction. So we've been looking at ways around that, and that's what I'm going to talk about today. I think we can get everything done in a browser tab about 95% of what you would normally do locally, which is pretty cool. My name is Mike Stish. I'm a firmware engineer at Goliath, and I split my time between the developer relations team and the firmware team. If you haven't heard of Goliath before, we're a cloud company, so we look at making it really easy to put microcontroller level devices into internet-connected fleets. And we rely really heavily on that for Zephyr because we're hardware agnostic. So the cross-platform support that Zephyr has is really important to us. We deliver a couple different parts of this cloud product. One is just the device management. Like if you have 10,000 devices and you need to get different builds of different firmware for different revisions, how do you manage that and make sure they go where they should? How do you do things like update sensor calibration to all those devices, or deal with getting debug logs back if you have misbehaving devices? And the other side of it is just dealing with all of that data, right? So you have this huge fleet. It's got sensors. You're sending data back. We have like time series data and stateful data. We make it possible to send that to wherever you want it. So if you want it out on like AWS or Azure or whatever, onto your own servers, onto your Influx or Mongo database, like wherever you want it to go. We take care of that kind of messy middle of getting the cloud side to talk to the embedded side in a way that is smart and works. And like I said, a big part of that is Zephyr. The problem is getting people to try it and to test out Goliath often means having to build Zephyr applications. And so we want to make that as frictionless as possible, because we find people that try Goliath like it, but you have to try it out the first time. And so one of the things that we've done there is we started hosting free monthly Zephyr trainings to kind of get customers and potential customers up to speed. And that went pretty well. And there's a hunger for that and appetite for that. But we found on those early trainings, we spent most of the training time just setting up the tool chain locally, which is not great. And so our most recent advancements on this have gotten us really close to a streamlined behavior that I'm going to demonstrate today. It relies on CodeSpaces, which is I guess it's a Microsoft product. CodeSpaces is owned by GitHub. GitHub's owned by Microsoft. It is free to use up to a certain amount of use. It's something like 120 core hours and, 16 gigabytes of storage or something like that, which we find nobody gets close to in a 3-hour training that we do. But it's not just this CodeSpaces product that I'm talking about. It's actually built on top of an open protocol called development containers, an open standard. And you can also run those with VS Code. I haven't checked. There's an open source fork of VS Code as well. I haven't checked to see if it runs in there, but I suspect that it does. Let us know in the chat if you know about that. So let's take a look at what CodeSpaces looks like. So I'm just going to go to this Zephyr repository that we have on the Goliath org under Zephyr training. We have several different applications set up here that we go over during the training. But we have this one folder right here called dev container, which does something kind of magical. And I am going to zoom this just so in case there's trouble seeing it. This code button that you would normally go to get the git clone URL has a CodeSpaces tab on it because of that dev container. And I can actually click and set up a new code space just on main of this. And what this is going to do is it's going to kick off a container build on the cloud somewhere. I have no idea where. And you can see it looks very much like VS Code because it is VS Code running in my browser. Now it's going to take just a minute in order for this to build, but I want to go and talk about how this repository is set up. So this is actually set up as a manifest repository.
Mike,
if
quick
you haven't
question.
heard-
Can you
Yes.
change the contrast a bit? Because that's just not coming through the video very well on your screen.
contrast?
The white and the grass. Yeah, between the you've got night mode going on here, and it's
Okay.
pretty grayed out from the video
Interesting.
from projections.
All right.
Thanks.
Yeah, let's see. Probably go here and then settings maybe, and then appearance and like default like that. Maybe. All right.
That'll probably help. And make the font a little
Okay.
bit bigger. Thanks. The back
right,
person
okay.
in the back row is me. Can't see it. So.
Yeah. All right. All right. So I was talking about how we have this laid out, and this is what's referred to as a manifest repository. If you haven't experienced that yet, I'd encourage you to go take a look at this talk I did last year at ZDS on manifests, which sets it up so that we lock everything that we're using, all the dependencies, to a particular version. So in this case, I can look in the West manifest, and you can see I'm including the Goliath module, which then imports a bunch of other modules, including like Nordic, Zephyr, all these things, and these are all locked to a specific version. And so this repository is going to install everything that you need tree-wise. The only thing it's not going to install is the tool chains, like the SDKNG, which is like the compilers, which I'm going to show you as part of our code spaces. All right, so in all of that talking, I've given this code space that I launched previously. And I'm sorry, Kate, I don't know how, oh, maybe I can do this. Light modern. Hey, there we go. All right, excellent. And I probably also need to make this bigger. All right, so this is VS Code running in a tab. This is our code space. It is running on the cloud. And you can see this has an app directory in it with all of those things that we were just looking at in the repository, including this dev container and then all of our sample code here. And I can even go into the app directory and I can right off the bat do a build if I type the correct letters. All right, let's see, 9160 DK, NRF 9160 NS. So we'll kick off a Zephyr build right there. Oh, no. Oh, I didn't give it the name of the app that I wanted to build. There we go. All right, so we kicked off a build, and we're not going to watch the whole thing. Oh, my, oh, my. Having troubles. Live demos, right? Did I type something wrong? Yes, I typed an F instead of a K. All right, this is totally going to work now. All right, so our build has started. That's pretty quick. So it does take about 40 seconds for this to load for me, and then the normal amount of build time right there. But it's a really great experience because all the code that people are building is right here. The code editor's right here. We're able to build it right here. The only thing that we don't have in this code spaces is the ability to actually use West Flash and flash the board. I guess you also don't have the ability to do like a West debug or a West attach. So that's that other 5 to 10% of the process. But for the most part, if you're having someone that's just starting out with Zephyr, getting them to actually look at the code, change the code, build the code is a big part of it. We have it set up so that we download the binaries locally, and I will show that in just a moment. But let's jump into what this whole kind of process is. So I mentioned before that any repository that has a .dev container folder in it and contains a dev container.json file is going to be treated as a dev container project that you can load up on code spaces. You can also run it locally, which I'll go into in the next section. But in this case, if I just look at that dev container.json file, it has pretty much everything in here that you need. There is one external file, which is on line 5 here. It says on create command, and then it runs a special command. I'll get to that in a moment. But the top 3 lines are what actually sets up the container for us. Goliath maintains our own like minimal Zephyr tools container. So it has like a minimal Debian on it, and then it just has the compiler tools built into it. On the next line, which is workspace mount, I am setting up a local workspace folder, and I'm telling it to bind that to the repository app folder. And if we look at how we have our YAML file set up for this, we're telling it put our repository into a subfolder called app, and so that's why we set that up as the same thing right here, app type bind, right, for the training folder. And then we set a workspace folder which says always start us off in the Zephyr training folder. And that's so that when we open the code spaces, that's what we get in our Explorer as the main thing. So you can see here's our Zephyr training. Here's the app folder that has all of those files. And then when it actually does a West update, it installs this deps folder with all of our dependencies. So there's the Zephyr tree right there. And we can see again in our manifest file, it's because we're using a path prefix of deps right here. So if we go and look at the next part of this is the actual create command. What this is doing is it's going, all right, we have a Docker container all set up. We have the image. We know where we're going to mount things. And then once the container starts running, it's going to run these tasks in order to kind of set everything up. So you can see, I'm actually going to go in here and work through it because I'd like to be able to highlight things a little bit better. All right, so I'm going to go into on create command, close this, and I'll make this a little bit bigger. Oh, there we go. All right. So in this, you can see the West init command. If you use a -L that says, hey, we already checked out the repository, so use a local, look for a manifest file locally and look for it in the app directory. So that just kind of gets West set up for what we've checked out. The West update, as I said, that is what is going to create the steps folder and pull all of our dependencies in. We run the West Zephyr export, which sets up our CMake. I'm sure it's a little bit hand-holdy for me to go through all this because people at this conference have probably done all this a million times. But we also want to set up our Python tools with all the dependencies that are required by Zephyr. I like to use the ll command to list files in Linux, so I've just customized our shell a little bit to be able to use that command. And then this is a handy one if you haven't seen this before. The West tool does include auto-completion for board names. So you can do tab auto-completion, but you have to set that up. So I'm setting that up as well. And then finally, I don't want all of these commands to be in the history. Like if you're at the terminal, you do an up arrow. And so this history-c kind of deletes that past history so that when users start our training, they don't accidentally get these commands coming up, which can be a little bit disconcerting. If I go back to my container, let's see, maybe in my slides. So right here. All right, so we've taken care of these first 4 lines, the image, the workspace stuff, and the onCreate command. We get to the rest of this, which is the remote environment. This kind of maps some environment variables from your local machine into the container. And then kind of the important part for your application is customizations. So some of the things that I always like to do, these refer directly to VS Code. So you can see that under the VS Code node right here. I always like to have the CPP tools, which is, just general linting and language server stuff for the C language. But also Nordic has some great extensions for VS Code for code highlighting and linting device tree and kconfig. And especially when we're doing a training and we're talking about kconfig and the device tree, for a lot of people, it's the first time seeing those things. Like having a linter code highlighting there is really great. So I make sure those get installed right away. The other settings here, this is basically to make VS Code less noisy. I generally use Vim instead of VS Code most of the time, and so I find the experience of like these pop-up windows really jarring. And so this just kind of quiets some of this, and it's kind of trial and error on getting that in there and getting that to work. So other than the customization of VS Code itself, there is one other thing that we did to customize the repository, and that is making it easier to get at the binaries themselves. So remember before I said you could not use West update because the USB port is not connected to this container where we previously built our code by maybe new terminal. All right, here's our code build that previously finished. You can see the output here. If I run a West Flash, I'm going to get an error here because we don't have the Flash tools installed and there's no board actually connected to whatever computer in the cloud is running this. But we added another command called West download. And so what that does is it goes and looks for the binary file that we're using, and it will create a downloads directory in our workspace, and then it will copy that with a renamed file name. Just a little wider so we can maybe see that. Okay, that's weird. All right, here's our file name. It has the board that I built it for, and then the app that I built, and then a timestamp so that if you're rebuilding and re-downloading, you don't get kind of confused on which thing you're building. Let's see, do I get the editor window back? Explorer, there we go. All right. All right, so you see the downloads folder right here, and in the downloads folder, there's the file that we just moved with our script, and you can click download and it will pop up a window for you to download it locally, which I'm not going to do. At that point, Nordic has a bunch of great tools like NRF Connect for desktop has a programmer in it. It also has a serial terminal in it. and they're cross-platform for Linux, Mac, Windows. So any users that come to our training, they can open this code spaces on their machine. They can download the files onto their machine, and they can use the Nordic tools to flash those files to the device, and then to see the serial output to the device. And we have basically no hangups for what operating system or computer, whatever browser you've decided to use, which is amazing. So I really appreciate that. I really like the ability to do that. If you're wondering about that custom command, let's see on my slides, I think I have some stuff here. You can see that I have just a subdirectory, utility, West command, and a couple of files in there. This is taking care of what's called the West extensions that lets you add these custom commands. You can find that in the Zephyr documentation. And then if I actually look at, well, let's look at the manifest file. Down at the bottom under self, remember we had this path to put it in the app path, but we also have this which says, hey, I have custom West commands, go to this location and look for them. And if I look for them in the browser right here, I can see the YAML file will tell you, all right, the file to run for the custom command is also in this folder, West download. The command you're going to use is download, and there's some more help stuff here. And then I'm not going to go through any of this Python stuff, or maybe I should just mention, like here, you can see we're actually filtering for which board we're building for so that we get the right binary name. So I think that's pretty important. If you're doing something like, I think Espressif generally needs to have its binaries merged together. So some things to look at for that. But if you need a workaround for something that doesn't happen because you're on the cloud and not at your local computer, this is a good way to do it. All right. The other thing that we take advantage of here, I showed all of those kind of initialization commands, like the West update. West update can take a really long time if you're pulling down the Zephyr tree and the Nordic NCS tree and all of that. And so if you don't want your user to have to spend like 5 minutes waiting for the container to build, or I guess more the first time, you can do something called a pre-build, which runs through all of that and then stores it as its own container in code spaces. And that's what we've done. It is really economical. Like it's a very small fee. You will be charged something for it by GitHub. The other thing that I like to point out is this, in general, this use of code spaces has great worldwide support. So we had previously been using a container-based solution, and if we had users that were like we had just one server, like maybe in San Francisco or something, if you have users that are like in Eastern Europe or Asia or like somewhere a long way away from there, it can cause bad latency. But we found that GitHub generally has enough servers in different places that people aren't dealing with those latencies. The code spaces are running in regions where they are. The other thing that I tried in looking at this is I really wanted to see what it would take to run this locally. And it takes almost nothing. Like if you open the folder that has a dev container folder in it, VS Code will pop up a thing that says, this has a dev container folder in it. Would you like to install the dev container extension? And once you do that, it pops up a message that says, this is a dev container. Would you like to build it? And then as you make changes to it, it's funny because it's almost like doing brain surgery on yourself. Inside the dev container that's running locally, you can update the dev container.json file, and then VS Code will rebuild it. You just have to be careful that you don't make syntax errors, or then it will not rebuild. It will be broken. Ask me how I know. But it makes it very easy to run these containers locally. There are some prerequisites. So I already had Docker installed, so you definitely need Docker installed. It will take a while to download the images the first time, depending on what you're doing. So just be aware of that. But once they're downloaded, then your images are cached locally. So it makes it pretty quick after that. The containers may or may not continue to run after you exit. So this is like VS Code on top of an instance of Docker. And so the things like, do I have a whole bunch of images stored from previous builds? And do I have containers that didn't get killed that may or may not be running in the background? Just know that some background knowledge about Docker is kind of necessary in using this. My next question, of course, was, all right, I'm running it locally. Can I use West Flash with this? And I looked into that a bunch. The answer is kind of yes. I'm on Linux, so I can run, I can connect it to my USB devices. It's not super simple, and I'll go over that. However, there is no support for Windows and Mac on doing this yet. So I think that's a Docker limitation, but I might not be right. One of the reasons that I don't feel comfortable running this on Linux in general is because you have to run it in privileged mode. So the changes to the JSON are pretty simple. You mount your USB endpoints or USB path from the system into the container, but then you have to tell it run in privilege mode. So privilege equals true. And that basically runs everything in a container as root, which I'm not super excited about. So I did this as an educational experience, but I wouldn't necessarily recommend it. Once I tried to actually flash, then it gave me the same error that I had when I demonstrated it just before, which is the flash tools aren't installed. So I used some tips from Nordic's container that they have in order to install the Seger and the Nordic command line tools. And I did this in that on create commands script. So it happens after the container builds. Now, if you were to build these into the container, then you wouldn't have to install them subsequently. The other thing you can do is if you have them installed locally in your system, you could bind mount them into the container. There's several different approaches to do it. And I did get it working. I don't know why I didn't put a slide in here, but you can do West Flash. It does totally work. It took me, I don't know, probably 2 hours to work through all of the stuff that wasn't in the container and rebuild it and all this stuff to get it working. It does work. But with code spaces, one of the big questions that we have is why not use WebUSB, which sounds like a great idea. If you haven't seen WebUSB before, I think the demos that I've seen for it are like you have a flasher tool where you don't install a dedicated app on your system, but you can just go to a web page and it will have awareness of a device that's connected through USB, and you can upload in your browser the binary and then it gets flashed to the device. So that's pretty much what we're doing with code spaces. We should be able to do it. I went and looked for it. And if you search the docs on code spaces for WebUSB, there are no mention of that. So not currently supported there. The other thing is my perception is that WebUSB is only really truly supported in Chrome. I saw that there might be some Firefox work, and I'm not sure where that is. But one of the things that I really liked that I mentioned before is that the cross-platformness of this is really desirable. So being able to not have to tell a user switch to Chrome or switch to whatever operating system is good. And so for now, we're fine with the workflow that we have where you download the binary and flash it locally. I think that this could be useful for a number of things for us. We're already using it. We've used it several times this year for our Zephyr training, and it has been great, really easy to support. People know VS Code already, and so they feel comfortable in it. It's been wonderful. A place that we're exploring, we have a number of different Zephyr samples in the Goliath module, Zephyr module, and it would be nice if we had a dev container for people that just want to like make small customizations and then compile the code and run it on their board to kind of like validate Goliath as an option for their company. And so we're looking at possibly adding that in. I also think, one of the places is kind of getting back to a snapshot in history, right? So if you have a client that has launched a product based on Zephyr, and that product's been in the field for a long time and the code has never been updated, and then they have a problem that needs troubleshooting, how do you get back to the build that was used when that was first released? So Zephyr is really good about that with the manifests and that manifest repository approach that we take with ours. But the thing that's different is we build with whatever tool chain is installed on the machine. So whatever compilers are installed on the machine. I could see a use case for these dev containers where you have a different Docker container for each version of the Zephyr SDK NG, so that you get back to the actual compiler tool that was used when it was originally compiled. I think that would be quite useful. But if you have use cases, I'd love to hear about them. Reach out to us on Goliath. A couple thank yous. I'd like to say a big thank you to Jonathan Barry, who is Goliath's founder and CEO, because he was the one that put together the dev container for this and said, "Hey, look, it works." And then he was the one that put together the code spaces and figured out the pre-builds for it, got all that set up and running. And so the DevRel team was able to come in, basically dump the training code repository in there and then start using it right away, which was super cool. If you do want to try out any of the examples that I did, the top URL right here, the Zephyr training on the Goliath org of GitHub has that in it. If you want to see what our training is like, even if you already know Zephyr, that's fine. Join us. There's a sign-up sheet. We do it every month, and it is free. Here's a link to the containers.dev, which is the open standard that we're building on top of. And then, of course, the code spaces, which is a GitHub feature, is listed here. And if you are ever looking to connect a ton of devices to the internet, you should give Goliath a try. It is free for individuals, and we'd love to talk to you about your use case. That is it for me. Thank you so much. Are there any questions?
Thanks, Mike. I've got the microphone and I'm just waiting for it. First hand is up. Go for it, Drew.
Yeah, so just real quick, do you have any sense for how GitHub code spaces specific this is? My understanding is there's like some, different third-party code spaces like things, and with dev containers, is it all fairly standardized?
So I think the dev containers is fairly standardized. If you go to this containers.dev, it's an open standard, and I believe it was kind of in Microsoft's intention, or at least when I talked to Jonathan Barry about this originally, he said it was Microsoft's intention to make it a standardized thing. I haven't tried out any competitors though, so your mileage may vary.
Any other questions? Let me go quickly check and see if there's anything in the chat. Sorry. No, not spying anything in the chat, so I think we're good. So again, thank you very much. And hopefully you can hear the applause from the room.
I did. Thanks
Mike.
everyone.
Appreciate
I appreciate it.
Take care.
Bye-bye.
And it should be unmuted. Good to go.
Yeah? Ah, yeah. Yep. Perfect. So you tune me out, or should I turn?
We're going to leave them unmuted on our end, so you can just monitor.
Okay, so I just leave it on now. Okay.
That would be the recommended way to do it.
Good.
Slides an?
Ja, habe ich. Okay. Welcome everyone to our talk. It's going to be about Delta updates, so how to make base system updates leaner for in-field updates. So this is happening in the context of the Civil Infrastructure Platform project. It's a real good example for broad collaboration in the project and beyond. But first of all, I'd like to introduce you to us. Who are we? So maybe Felix, a few words about yourself.
Yeah, I'm Felix Mössbauer. I work at Siemens Technology as an embedded Linux consultant and developer. And I'm lucky because I'm allowed to contribute to major open source projects, not just for fun, but also for profit. And apart from that, I develop a lot of in-house tooling we use at Siemens.
Yeah, and basically, I'm Jan Kisker. I'm doing basically the same, just a little bit longer, I think, by now. I'm also part of the CIP project, leading there the CIP kernel group, or being the chair, so to say. The work is done by other people. I'm also maintaining inside this CIP project the CIP core layer. What it is, we'll find a few words later on. But also beyond, I'm maintainer and contributor to various open source projects. I guess you maybe have seen some talk of me before here in that context. So our use case for today is about robust in-field updates. So who of you are operating devices in the field that needs over-the-air updates? Okay. Yes, I guess you're on the right talk. So there are many of these examples by now, and we just picked one here from the fancy domain of car charging, e-car charging. So you have these charging stations all across the board for various purposes, in-house or public charging stations, and they are quite complex systems by now. They have software for the actual control of the charging, but they also have a UI. If you're charging the folks who want to get the energy there, you may have an interaction with the users. You have not only just one controller there, possibly many, and they have software. They have to be updated, obviously, over the air. They might be remotely placed and not connected to some wired network. And as I said, the systems are complex, so what we are shipping to these devices are not just megabytes anymore, it can easily be gigabytes if you do the complete refresh of the system there with all the controllers inside. You want to do that normally in a consistent state, so you're not shipping the bits and bytes individually, but you're rather shipping a consistent state. It has been tested upfront, because the worst thing that can happen that one of these stations go offline because of a wrong update, and someone has to go there and press the reset button, or even worse, come with a service stick and reinstall the device there. So this is a critical use case. Still, as they are remotely and they might be connected via a wireless network, it can be, they can be limited bandwidths, or they can be even limited and charged bandwidth, so it can be cost factor to reduce how much you actually transfer over the line. So this is roughly the problem space that you can find also in other domains. And now the question is how to make that case easily adoptable. We are implementing a lot of these devices in our company. The CIP project have many users who are implementing that. And the key problem for us was, or the key question for us was how to make this adoption of the pattern easier for everyone. So the CIP project, just to introduce it briefly, in a nutshell, from a top-level view, we are our mission is to provide an industrial-grade Linux. That means we are not inventing the wheel from the beginning. We are basically building on top of many, many existing open source projects. We are rather looking for the gaps in the domain of industrial and critical infrastructure adoption of such kind of complex systems, and then jump in when no one else is looking after that and fill the gaps by contributing, or if there's really no one like this or no project like this existing already, also creating new projects and then operating them. We provide also, and that will be also about the talk, pre-integration patterns. So none of these systems you can just install and run just by adding your own file on top. It's more like customization and tailoring. If you have different hardware, you have different applications running, you have a different combination of things. So what we can provide are the pre-integration patterns so that you can benefit from that and do the 90% yourself, the 90% from the pattern and the 10% only yourself. That's the idea behind it. And then obviously comes the longevity of these integrations. These devices, they don't live like your mobile, and even the mobile devices by now have a longer lifetime. So these have to be maintained in the field. Updates have to be provided, whatever strategy there is. So when there is a gap in the maintenance of these components, we also look into ensuring the longevity of them by working again with the communities or by doing it ourselves. So one of the examples is that we have a super long-living kernel for this purpose domain in our portfolio. And last but not least, this is more important these days, we're also working on the security certification of such an integration, the pre-certification. And what you're certifying there is a product, the whole integration, but we try to provide as many reasonable, reusable building blocks for the certification process. Now, specifically for the problem domain I mentioned before, there are two work groups in CIP which have direct impact on that. There's a CIP core work group and the software update work group. So what are they providing or working on? So from the CIP core, we have a pre-integration layer where we pull together relevant components for software update pattern for secure booting. Here we are using the supply chain of Debian heavily. So basically this integration is providing an image build environment and a customization environment for Debian packages, or an ad hoc build environment for Debian packages if there are none in the upstream communities. The integration pattern that can be described this way then addresses the key elements of securely booting such systems and, well, obviously remotely updating them. So that is then also described in this layer as a reference. So we are using here Debian. We are, in some cases, have to adopt to how Debian is doing things, but the whole concept here is obviously also transferable to other environments. So it's a lot of similarity with how Yocto are building things. Conceptually, it's not a one-to-one copying over, but if you understand the concepts here, you can transfer them also if you're working on a Yocto open embedded environment. So what are the key building blocks for us in the software update workgroup? Well, again, there are many options on the market. We choose one, the SW update tool, which is a service running on the device to manage the update, to orchestrate it there. That's one element. There are others, Rauk, for example, but this is how we started a while ago and how we customized. And then there's a backend service, an orchestration service to manage the fleet of devices, so to say, or a fleet of updates. It's a WFX framework, which is, well, a core, execution core for orchestrating, as I said, the updates things. This is where we are working on and integrating. Again, we are collaborating here. SW Update is not a CIP project. It's a third-party development. We are contributing there. We are integrating and helping to make it more usable. WFX, by chance, happens to be right now a Siemens project. We are working on transferring this as well. So that's the building blocks, the key building blocks on the technical side. The approach we are taking here for have a reliable update is also very conservative. It's a classical dual copy update pattern that we are applying here. That means you have always a running version of your software stack, and then you have preparing a new version that you try out, and then you can fall back always to the existing version if the tryout fails in the field. So for that, we are enabling, or we have enabled SW Update with a corresponding handler to manage the switchover. We have brought forward a project for doing this control during the boot time, EV boot guard, so that you can select the paths there. That's the straight way forward to do the control there. And the pattern we are using here is an immutable rootfs, and on top an overlay to manage, well, the customization, the specification of a device when a private or device individual data has to be stored. All that also can or has to be done, obviously, these days securely. So secure boot has to be applicable here. So we are following, wherever possible, the EFI path for that. So System Ready, you may have heard about it, is providing that not only for x86, but also way beyond. So we are building on top of that for secure booting. We are also have pre-integrated, which is again an existing feature of SW Update, but you have to be aware of that, the signing of the update artifacts, so that you're not executing a random stuff being downloaded to the device. You actually can validate that it is coming from the trusted source before then applying it. We have pre-integrated disencryption, which is, well, also no rocket science, but it has to be done so that everything which is modifiable on the device is stored in an encrypted partition. And last but not least, we are also validating the immutable part, the rootfs, in this case with DM Verity, also pre-integrated. All in all, no rocket science. Maybe you are using part of these already or something similar, but in the end, you have to pull them all together. And if you have to pull many things together, there can always be a mistake or some forgotten element. And if you forget something in this critical thing, well, the device is either insecure, not reliable, or both of them. So this is the key element about that. So a few words on the update schema. I mentioned it already. We are using here the classic AB schema. So you always have up to 2 full images from your updatable elements. So that means you have 2 kernels that you want to boot and 2 rootfs's. So the kernel, we use the unified kernel image format for that in order to have a container which contains the kernel, an init FS if you need one, command line settings if you have something, or even a device tree override for what the firmware is not providing properly for the device. That thing comes into one container that can be signed. So you have that element is the first thing coming after the bootloader. And then you have the rootfs containing everything that you need to operate the core system in order to, well, also operate the updates, obviously. And that is in an immutable squashfs. That can become, obviously, quite large unless you then start to split out and move certain things into additional partitions which can be separately updated. But yeah, normally you have a rather large system here. And that's now the key point. Even if you have already split kernel and rootfs, if a single file changes in the rootfs, you may have to replace everything. Also, something technically, it's a technical reason for that. The kernel containers UKI has a logical correlation with the rootfs because it, for example, for the DM Verity, it has to contain the root hash for the rootfs. So if you're updating your kernel, if you're updating your rootfs by just replacing a file, you get a different root hash, and because you get a different root hash, you have to redistribute an updated UKI image. So you can see already a single change can impact the whole chain significantly. And there comes the question of, why not use or apply delta updates? It's also an old feature of SW Update, and the concept is even much older. So compared to the classic way of doing the complete image build and the complete image deployment or artifact deployment every time you do an update, we only want to really distribute the delta between the current version and the new version. So what has to be done for that? That is the key question. Because in the end, you have to generate, first of all, these delta from your build process, in addition to the full image that you may still generate. And you have to decide on how to distribute the delta and how to apply it there. So these are the key questions. Is it possible to do that, Technically, people were talking about it, but how to implement it actually? Can we keep up the security along that? So if we change this property, is the signing procedure we have still applicable? And also, how do we have to change the build process of our images to make that as smoothly as possible generatable? If you have to adjust the build process for every other update because something is slightly different, this will not be used in practice. So with these questions, I would hand over to Felix because I think he has the answers.
Let's see. So when you start investigating about how to just update the delta you have, you will see there are a couple of options with all their pros and cons. And there's also a great talk by Stefano Babik, that's the developer or maintainer of the SW Update project, about which options we have there, which are suitable for SW Update, which are not so well suited. And the most promising ones are the ones I show here. So in short, an interesting project is the zchunk or zchunk project, which is at first just a compression format. But the interesting thing hereby is that it compresses in a way so that you can generate a header with all the checksums of the blocks, or like bigger blocks then. And then there's a tool which just takes a checksum file, compares it to an existing file, and then just downloads the delta, basically the checksums that are not yet there. The project has another advantage, that you don't need to compress. That means you can also do that on already compressed files, and by that avoid some issues you have, like recompression is almost always a bad thing, and so on. Another project is the RDiff library, or RDiff tool, which uses the librsync library, which can be used to generate a delta file, which then can be shipped out of band. That means you can, based on two files, just generate a third one, which contains the delta between both, and then when you have the original file and the delta, you can generate the new one, and you just need to ship this small delta file. And it doesn't matter how you ship it. Like, you can put it on a web server, or you can also put it in your SW Update artifact, or you can transport it by any other mechanism. Finally, a project that was mentioned a couple times also here at the conference is the CA-sync project. This is a combination of the rsync algorithm with a content addressable storage. But unfortunately, that's not very well suited for the embedded use case, because firstly, you cannot simply distribute an update artifact, as this content addressable storage is a huge set of files and a directory structure and so on, which you need to put somewhere. And second, the download itself uses many requests, and if you need to do HTTP requests, especially via HTTPS on an embedded device, it can be quite costly in terms of the compute power that you need, and also by that, the time the update takes to be performed. Let's first have a look at the RDiff handler for SW Update, which uses the librsync mechanisms. Why do we start with that? Because it's the most simple pattern you can do, as you basically don't need to change anything. The first step hereby is to build the image. Like always, both with Yocto as well as with ISA, which we use in the CIP project, you have a build pipeline, and in the end, you get a couple of artifacts out of that build pipeline. One is a WIC file, which is just an image you can flash onto a SD card or a disk and then boot from that. Important for the first deployment, but after that, not so important anymore, because you want to do updates and not whole reflashing. Second, you get out an SWU file, which is exactly this update artifact, which you then transfer to the device. So this will be our starting point also for comparing the next, or having a look at the next algorithms here. So that's this SWU file here. To generate the delta file now, you need a signature of the old image, so an RDiff signature, because, as said, you will pre-generate a delta file, and by that you need to know against which to generate this delta file. So here first you generate it, and then you create a new SWU file, which contains, of course, the metadata as well as the delta file there. Then the next step hereby is to upload that file to an update server. I'm not sure if everyone is familiar with the pattern SW update uses, but usually it's that we have a backend and a front end. And the backend here is a server, or it can be a management system where you do the device management. And then you have the device, and the device polls the server if there are updates or not. So here first you need to upload the new SWU file, which only contains the delta part, to the server, and this file is quite small, as of course it only contains the delta. The third step hereby is to download that file to the device. So usually the device just polls in regular intervals, or you have maintenance windows, and then during that maintenance window, SW update polls the server, and if there's a new one, then it starts to apply that image. It downloads the image and then applies the image. There's one important detail to mention here. Now we need to combine the old image and the delta file to finally generate the new image. That is a bit different, like how you would do it with a regular rsync. And the reason for that is that you have two partitions. Like you have the currently running partition, and you have the partition you want to update, which you then boot into in the next reboot. And you need to create the new image on the currently non-active partition based on the old image, which is in the currently running partition, so that needs to be read-only, together with the delta. And that also brings us to, or directly brings us to, the advantages and disadvantages. The good thing hereby is you can apply that pattern to the already existing infrastructure you have. Like the update server doesn't care if this is a delta file or not, because it only gets the SWU file and needs to ship that or provide that, but there is no additional files needed. Also, as Jan mentioned before, we support signing these SWU files. And the reason for that is to make sure that only a trusted provider can actually provide an update file for a device. And here we can directly do the same signing as with the full update file by just doing the signing at the build time, which is very good, because then we don't need to hand out any cryptographic material to a third party who runs the update server. Also, you could do an offline update via a USB drive, like with a rescue stick, for instance, and by that support use cases where you don't have network connectivity. That might not be the default use case, but it's supported by that pattern. And finally, when talking about the update sizes, the RDIF algorithm has the disadvantage that it only works well if the image is big and the delta is small. But these are just qualitative measures. How do you know how big your update will be? And here, in this case, you can simply compare the full image update, so the SWU file here, with the delta update file and see which one is bigger. And if your delta, for whatever reason, is bigger than the original one, well, then you just don't do a delta update. Then you just ship the full image update instead of the delta. But a major drawback hereby is that you need to know what is running on your device, as this needs to match the delta image you generated. So you cannot do image skipping updates, but only can do incremental updates. A slightly different version of the same pattern here is the RDIF handler with an on-demand generated image. That means we have the same workflow, but if you look here at what we do at the build system and what we do at the update server, we do the generation of the delta image at the update server. So hereby the device just tells the update server what checksums or what kind of image is currently running there. Then this RDIF signature is uploaded to the update server, and the update server generates a new matching delta update SWU file based on what the device has. This sounds like a good idea, but in practice, it's not really applicable. And the reason for that is that while you're able to support different versions of the things that are running on the device, you need to generate the update file on the update server, which is usually not under your control, or at least not under the control of the vendor, like us, but is running at the customer side. And as we also want to sign these updates, now we need to hand out cryptographic material to our customer, which runs the server. And this, in practice, is often not possible. Also, the path on the left, which is in this dotted box here, is not supported by the SW Update API itself. So you need to do that somehow out of band. So in practice, this sounds good, but often it's not really working. But anyways, I wanted to show it just to highlight how flexible these approaches are. The third approach hereby is using the Z-chunk handler. I showed it before, which uses a totally different strategy while still using SW Update to perform the update. So first, at the build system, you again start with the SWU file with the new image or the full image. And then you generate a new SWU file by removing the original image and replacing it with the Z-chunk image header, which is just a file that contains the block checksums of the image. And of course, this file is really, really small, like it's a megabyte or less. And that's the only thing you need to put into that SWU file. Then you upload two artifacts to the update server. One is the SWU file that also will be downloaded later on by SW Update, which is small because it only contains the checksums, as well as the full image. And hereby, I mean the full rootfs. And finally, the SW Update, which is running at the target, then downloads the SWU file here from the update server, pretty standard, like always. And then via a handler, triggers a download of just the chunks which we don't have on the device yet. These chunks are then downloaded from the HTTP server here. And you might think that if I download chunk by chunk, that's quite inefficient. Yes, that's true. But there's an optimization, and this makes quite a big difference. So this download here uses HTTP range requests. That means we can download whole ranges of chunks, even non-continuous ranges of chunks, in a single HTTP request. That also means if we do HTTPS, we only need to set up or do the handshake once, and can download all the chunks no matter where they are in the image. It's quite a big advantage. Now you might ask which HTTP servers support that HTTP range request feature. And the good thing is basically all, even the Go built-in server supports that. And the reason is that all the big video platforms like YouTube, they use that. So it's a pretty commonly used feature which we rely on here. And then also this handler combines the old image with the Delta chunks we just downloaded and writes that to the new partition here. The advantage hereby is that it's very flexible because you don't need to know which image you're running on the device. Also, it's supported in SW Update, no special API needed. And regarding the update size, you don't need to have a look at if the update is small or big, because as only the chunks are downloaded, the update can't get any bigger than the original file, which is a huge advantage if you really don't know from where to where you are updating. But the disadvantage is you need to upload 2 images to the update server, so your update server needs to actually support that. And second, this path here, the Delta downloader, currently is HTTP only, specified by the Z-chunk standard, or Z-chunk implementation. And that means you need to have somehow an HTTP path between these 2 entities, which is not always possible in all use cases we have. Now, a very important thing to mention when talking about these updates. The most important thing when talking about Delta updates is to make your update as small as possible, because if you generate a huge set of Delta there, the advantage to do the Delta update is minimal. So one important thing here is to build things reproducible. As I said, both with EOSS as well as with Yocto, you build everything freshly. And here you need to make sure you build reproducible, as otherwise you will have delta in things which you didn't touch actually, just because they can't be built reproducibly. So here let's consider that the red package is the one where we have our real delta because we changed something, but then all other packages should stay the same. A next thing is that you don't ship packages, but you ship a rootfs. That means first you need to install all these packages into a rootfs. And you might be surprised, but installing reproducibly is a totally different story, especially when talking about Debian, where you have post-install scripts, things might run in a different order. So you really need to put some thought into how to install reproducible so that also this delta is small. We at the civil infrastructure platform, we implemented some patterns there which help the user, like also fixing the file timestamps so that you don't have changes in all the files just because the timestamps of each and every file changed. Then for our read-only rootfs, we use a squashfs. This can also be in a DM Verity container, but the rootfs itself is a squashfs, and this is compressed to make it small. But there's a thing compression algorithms are good at, and that is reading the whole information they get to then generate the best possible compressed artifact from that. That doesn't help us here because if we change a little bit in the input, likely everything in the output changes, so our delta will be huge again. So what most compression algorithms support here is a so-called rsync mode or rsyncable flag, which performs state resets. That means only a bigger chunk is compressed, and then the next chunk is compressed, but the information from the previous chunk is not used to better compress the next chunk, and by that you also limit the chunks that actually changed. And the final thing is you will generate an update artifact, which usually is compressed again. So here make sure that you don't compress that, otherwise you have exactly the same problem as before, and double compression usually doesn't make any sense anyways, as it doesn't make the artifact smaller, it just changes the entropy in the artifact, which we want to keep as low as possible. So let's have a look at what is already implemented and what can be used as of today. So first of all, the required components are all packaged in ISA core, and you can use that. And then we have support for both the artif algorithm as well as the Z-chunk algorithm to generate these artifacts. Unfortunately, it's currently on the mailing list. There's a branch. I put it in the caption here. It's not yet released because in CIP, if we add a feature, we also want to keep that stable. So we want to do it right. So that's why it's still under review. But if you're interested, just use that branch and play around with it. Otherwise, in the next week or 2 weeks, it will be integrated anyways. From an SW update perspective, everything we need is there. The project itself supports it. The update handler supports it. And we have support for chaining handlers. Why do we need to chain handler? Because the first thing you need to do is to check where to apply the update, like to which partition. And the second thing you need to do is how to apply the update, like with the delta handler. And when looking at the commonly used backends for RDIF, there is no change required because you still have only this one SWU file. For that chunk, you need a backend that supports it. With the Hawkbit backend, that's not the case yet, but you still can make it work on that backend by just shipping the Z-chunk artifact, so not the SWU file, but the artifact from a different URL. And it doesn't need to be on the same server. You can also put it on a CDN or wherever. With the WFX backend, everything is supported out of the box. And we also tried that, so it's actually working. Let's come to a frequently asked question, how about Delta updates and security? So the building part is clear, not so much changed here. Anyways, we just look at the Z-chunk part as with the RDIF part, the workflow is pretty similar to doing a full image update, but Z-chunk is a bit special. So the first thing here is that in this new SWU file, you have, of course, the SW description file, and this file assigned, so you can check a signature. You can both do that at the update server as well as when downloading the artifact at the target. Second, if you now need to have an HTTP path between here and so between the update server and the device. And of course, everything is secured there, but you might have more complicated login patterns here, which are not supported by SW Update, which you also then need to do via this handler here, which is a very minimal piece of software. So it's tricky to implement there. But you can work around it by just using a local proxy, which is running on the image, on the target, which does which acts as a reverse proxy and does all the complicated cryptographic stuff like HTTPS, the login into the backend and things like that. So no problem. Finally, you now have two artifacts. One is the SWU file and one is the Delta file, which you then download from the, this file here, which you then download from the update server. And now you could exchange or replace this file here as it's not signed. But this is also not a problem as this is protected by the checksums you have in here. So basically when we know which chunks to download, and then we download a chunk and see that the checksum does not match maybe between this one here and the thing from the checksum headers here, then we know that something incorrect is going on there and we can stop the update. So also that is perfectly safe and secure. And finally, the new image is, as I said, if you do secure boot, you also want to make sure that the rootfs cannot be replaced, so you usually do a DM-Verity container around that. But as we recreate exactly the same image as in the beginning, just the way we recreate it is different, but it's bitwise identical. Also, the DM-Verity hash still matches. Next topic is Delta updates and secure boot. Why does it work? If you think about it, it's rather easy to understand why it works. So the workflow or the boot flow is exactly the same as Jan presented before. So first we have the bootloader, which is in our case EFI bootguard. It's just an EFI binary which is signed with the secure boot keys. This then selects, based on a configuration file, the next partition to boot from where the UKI, so the unified kernel image is. And also this is an EFI file, so we also sign it just with the secure boot keys. When we now do an update, currently we only partially update or Delta update the rootfs, which is the big thing, but we fully update the kernel. This is also an important thing. We could also update the kernel with a Delta algorithm. Currently we don't do it because the kernel is rather small anyways. So there's not a big benefit of doing so. And this kernel here in the init.rd has the DM-Verity hash. So we then check the DM-Verity hash for the rootfs that should be used next and mounted next, and only if that matches, then we mount that. But as said before, the DM-Verity container is bit by bit identical from the original image, like if we would do a full update, so that also works. And finally, we have a data partition, which is usually encrypted, so that no one can read the data that is generated while the system is running, and that just uses the hardware or firmware TPM to do the key handling and then decrypt that stuff. So let's summarize things. I guess time is almost over anyways. Using Delta updates is more resource efficient, and it's you get a bit bigger benefit if the image is big and the changes are small. But with the Z-chunk handler, you also benefit if the delta is not too small. It's always better than just doing a full update. It's still reliable, so we still support this dual copy update pattern. You don't have any impact on the security, as I showed. But unfortunately, it's also not a free lunch. Like, you need to make sure what are the pros and cons of each algorithm. Like for the RDIF algorithm, the advantage is that you can pre-generate everything. You can transmit the SWU file out of band. No need to have a direct connection to the update server. While for the Z-chunk, the update pattern is easier, as you don't need to pre-generate things, but you need a way to communicate via HTTP between the update server and the target. Then I want to give a huge shout out to the Toshiba colleagues who did most of the implementation there in CIP, as well as to my Chinese colleague Wang Qi, who tested really thoroughly all the patterns we have there and We iterated quite a time with the Toshiba colleagues to finally get a thing that is both robust as well as easy to use. And by that, we are done, and I hope we have some time for questions. Do we have a microphone?
Wait. Do we have a microphone?
I think, yeah. Because we
Mike?
have a remote audience as well, and then it's easier for them.
Thank you. Let's turn it on. Yeah.
Otherwise, you can also
Yeah.
ask the question we just
Use
repeat.
mine.
Hello. Hi, thank you for your presentation. A little bit related to this topic, maybe that's why I think you did not mention is resume or start over of downloading the chunks, if we want to call it chunks. Do those technologies support that? So if you are downloading a chunk or part of it and, I don't know, you lose internet connection, then can you resume downloading from where you stop it later? Thank you.
Do you want to answer, Jan? Okay, so it depends on the algorithm. For SW Update itself, there is support to resume the update as far as I know. But for the Z-chunk handler, if I remember correctly, it's not yet implemented. In theory, you can also think about optimizing the whole pattern a bit. Like, as I said, we need to recreate the whole image on the new partition. So we write always, when we do an update, we still write the whole new partition. But what we could do is read first what's in there, and only if there's a diff, then we just download that part and make a change there. As far as I know, it's not implemented yet. So that would be our next step to do. Other questions?
Okay.
Seems not to be the case. Then, thanks for having us.
Thank you.
And enjoy the conference.
in our project, and we find out yesterday. I'm not sure what you guys, but there was a comparison between.
Yeah, I was in this talk as well. Yes, yes.
I was not there.
Oh, okay, I was there. Yeah.
So we use it for embedded, but we use RAW plus CAC together.
Okay.
So when you say that's not suitable for embedded, I get what you say.
I mean,
but I wonder how much concern it should be.
maybe no, you shouldn't be concerned. Our setting is a bit different. So what we do is we use SW Update and not RAW to apply the pattern there. And one key design decision of the SW Update pattern, SW Update project was to have only very little artifacts which you need to upload to the update server, because these you need to sign, and there you need to check the signature and so on. And if you now have a content addressable storage like with the CA sync, where you have hundreds or thousands of files, that doesn't fit into the picture. So for us, it's not suitable, but for embedded, like if you go with RAW, your mileage might vary.
Yeah, we are fighting that fight, but it's working for now.
And especially if you have bigger, I mean, SW Update, we use it for Linux updates, but you can also use that for embedded, for real microcontroller updates and so on. And there they really care, or really low-powered Linux platforms, and there they really care about the efficiency. Like for the things we update there, cryptographical stuff is usually not an issue.
Yeah, thank you for.
Yeah, you're welcome.
You said when you're building it, to not get this another checksum, because when you build something, you get the time inside.
Yes, exactly.
You use fake time and then the Git repo time as.
Well,
So then you can read.
Source data epoch,
Yeah.
both on the build packages
Yeah.
part, but also on the imaging stuff.
Yeah.
There are some infrastructure for that.
Yeah.
Conceptually the same.
I mean, there are two things. One is to try to have as little change as possible, so use source date epoch to generate the files with the correct timestamp. Second is that we have a post-processing step where we align the timestamps and clamp that to the thing. And the third thing is that as we use SquashFS, there you also need to make sure again that the timestamps which end up in the SquashFS are still according to the source date epoch.
We don't have an update server, but we have kind of looking at the whole package as just an embedded microcontroller, but it contains the, we have one file for the root file system and the kernel and the DTS, like a FIT image.
Yeah, for U-boot probably.
Yeah, because then we put that into dual A and B
Yes,
size, right? So
also
we
works.
can select.
Yeah.
And then we have the application files as well, which we build everything and then it's used the.
So for us, the reason why we do EFI booting is that we can easily port the same application across architectures, including the update workflow. Yes. Yes. Well, otherwise, if you need to do it for x86 totally differently than for ARM, because on x86 you cannot do U-boot with the fit images, it's an additional thing you need to do. Yeah. Yes. Okay. Okay. You have another question?
Ich wollte nur mal
Ach so.
Ich glaube, wir haben schon mal telefoniert. Ich bin von Waldmüller und wir wollten ja euren EFI-Bootguard mal
Okay.
zumindest, genau, und irgendwie hatten wir mal telefoniert. Ich dachte, ich sage einfach mal Hallo.
Ja, cool.
Ja, genau.
Hi, Felix.
Hi, Lukas. Ja, hi. Ja.
Du warst jetzt auch im Talk drin, oder?
Genau, ich habe
Ja,
auch
okay.
zugehört. Ja, genau. Wir benutzen auch SW-Update, aber wir machen keine Data-Updates. Also Kunden in der Regel.
Hier auch noch viel zu wenig.
Also wir auch nicht.
Das kommt jetzt hoch. Ja, genau. Können wir mal abgehen.
Okay, we can start. Check. Hello everyone. Good morning and welcome to Open Source Summit. In this talk, we are going to see how Zephyr RTOS is used or act as a electrical vehicle supply equipment. In other words, in short, it is called as an electrical charging station, and using the open standard called Open Charge Point Protocol. So my name is Saravanan. I'm a part of Linumus. I'm working as a software engineer, or the embedded software engineer at Linumus. Over 13 years of experience in the Linux, working in a Linux. I'm a developer and a contributor to the open source projects like Linux kernel and Zephyr RTOS. About Linumus, it's a software servicing company which provides embedded software development and consulting and training in embedded Linux and Zephyr RTOS project. So we do servicing in the range of bootloader development and then kernel development, new boot support packages, and also the device driver development. I live in Berlin. Okay. Here is the summary of this talk. First, we will check what's an electrical vehicle and how the current state of the infrastructure, charging infrastructure, and what is the limitations currently having, and then how does Zephyr RTOS helps to improve the limitations for achieving the better charging infrastructure. And this talk is primarily focused on the Open Charge Point Protocol. It's an open standard specification, so we will look into the what is Open Charge Point Protocol or the OCPP, and then we will have a brief look into the specification internals. After that, we will have a look into the OCPP implementation, the native implementation of the stack and the Zephyr RTOS, and how to consume it in the application layer. And after that, we will have a look into this electrical vehicle supply equipment standards, which is mainly used to connect between the charging station and EV for handshaking and delivering the power. And finally, we will look into the current state of OCPP in the Zephyr and the future work. Okay, so electrical vehicle is an emerging market because of its advantage of environment friendly, but there is a limitation because of a lack of charging infrastructure. So electrical vehicle supply equipment or the charging station is simply called as a charging station, which is used for the supply of electricity or the energy to the electrical vehicle which utilize that to the battery charging. In comparison with the gasoline vehicle, like petrol station, which will takes a few minutes to refill the fuel, but one of the limitations with the electrical vehicle is the amount of time it will take to recharge the battery is very huge, and also it occupies the parking space until it gets recharged fully. So, but one of the advantages with the charging station is which is a portable and it can be installed, easy to install in most of the parking place. So, is it really need to be installed in the parking place because like we cannot make it installation in the petrol station or the gas station because we need a more parking lot. So the better place to install the charging station is the existing parking place where we can utilize that. So in the nutshell, we need a more and more lightweighted distributed networks, so where we can employ that instead of handling the bulky machine which can handle the multiple port, like 100 ports of charging vehicle, it can handle it. So we really need a distributed network where we have the parking lot, where we will have like the highways or else the hotels or even the working office space environment. So we have seen, so what is the limitation and what we really need is a distributed charging infrastructure, and how does the Zephyr gonna helps with this distributed charging infrastructure. So microcontrollers are more suitable for the lightweighted applications, And then, yeah, for the microcontrollers, we obviously have one of the choices, Zephyr ATAS, which has more advantages in terms of it supports a multiple Ethernet interface, and then the other interface, which we'll go and see. The Zephyr ATAS has its advantages, like it has a native implementation of TCP IP stacks, and then it can be directly used to the Ethernet controller. And apart from that, we can use the internet infrastructure for the Wi-Fi controllers, and a lot of Wi-Fi controllers which supports offloading, which means we can send the payload, and then that TCP or the IP packet will be framed by the offloading controllers. So we have the support in the Zephyr ATAS for the offload socket option also, so which will reduce the burden on the microcontroller, which can focus on the application side. And one of the requirement for the EVSE is like when we are going to install the charging station in the highways, like where it is in the remote areas, we have a lack of internet infrastructure, so we can use the modem as one of the internet-facing interfaces. So Zephyr ATAS supports a modem like one single die solution like NRF, where we have the application processor application CPU, and also the modem can coexist in a single die. Otherwise, also the Zephyr supports other external modem which works on the CMUX or the PPP or AT commands. And then Zephyr ATAS itself supports the variety of architecture, supports like Extensa, RISC-V, ARM, and also the because of that, we have a more and more platforms supported. So if you want to go proof of concept, which will be helpful, like the existing platform with the Ethernet support or Wi-Fi can be used as a proof of concept before going into real product use case. So as a EVSE really wants to measure how much the power it is, how much the power or the energy which is delivered to the EV, the charging station should employed with the energy meter. So most of the industrial energy meter supports digital communications like Modbus or Modbus, and then the UART or other serial MBus modules. So thanks to Zephyr ATAS, which supports the native support of the Modbus as well. And at the end, we are going to have the support for the Open Charge Point Protocol native stack in the Zephyr as well. So collectively, we have a lot of advantages why we should go for the Zephyr ATAS, how it would be helpful for improving the charging infrastructure. In addition to that, we do have a RFID reader, which probably with the NFC stacks, and it's going to be integrated or the merge soon into the Zephyr ATAS. So we have seen so far what is drawbacks in the charging station, how does the Zephyr ATAS going to help in that. So now we will briefly check into the Open Charge Point protocols and what is it is, why it is really needed in the electrical vehicle supply equipment or the charging stations. The Open Charge Point Protocol, or simply called as OCPP, is an application protocol which is used to communication between the electrical vehicle supply equipment and the central management system. So we know the charging station is to provide the power to the electrical vehicle, but what is this central management system is a kind of a backend server which will handle the user entity and how much the charges, how much energy has been used by the consumer on different charging station, and based on that, the billing will be generated. So these database will be maintained by the central management system. So it is, the Open Charge Point Protocol is established by Open Charge Alliance. It is established by, in 2009. And since it has the advantage, like it is designed to be the free open source and also interoperability support, it becomes a global benchmark for throughout the EV industry to adapt the OCPP in all the charging station, I would say. Okay, so does OCPP really need in the charging station is a question, because when I have a private charging station which can directly connect to the electrical vehicle, then there is no need of charging the OCPP protocol. But really, when we have the public infrastructure installed, the EVSC, then we need a communication back to the backend, which is supported by this open charge point protocols. So I would say the open charge point protocol is not an option for the public infrastructure, and also I would say it is recommended for the private infrastructure as well, private charging station as well. Why? Because we need a more and more distributed net charging infrastructure. For that, even the private contributor to the charging infrastructure, which will help the whole EV industry, so or the EV segment. So when the private charging station is not in use, it can lend for the public access, and based on that, it can boost the EV segment or the charging segment. So OCPP has been developed in the with the multiple versions, starting from the V1.4 and 1.5, which are already obsolete, which supports a different messaging format, which we will going to see in the next slides. Currently, we have the support of version 1.6 and version 2.0.1. And with respect to current presentations, we limit the scope of version 1.6. Okay. If you are new to the electrical vehicle supply equipment or the charging, these are all the abbreviations which we'll be going to use in the following slide. So it would be helpful if we can see these are the observations. So CP meant for the charge point, and CPU is a charge point operator who can handle the database or the maintenance of the central system, and CS is the backend system, which is central system, and then ID tag. Unique identification used to identify the user, maybe the access card where we can read the ID tag. And OCPP is an open charge point protocol. Then there are two messages which is framed by the OCPP. The PDU is a protocol defined unit, and RPC, which we will see in the next slides. Okay. The profiles and messages. The basic communication between the central system and the charge point are based on the predefined protocol defined unit, or simply the PDU messages. So these are the basic building blocks between the communication between the charging station and the central system. So there are approximately the version 1.6 supports 29 messages. We are not going to see all those messages because of the time constraints, but these messages are grouped into a profile based on the features and functionality. Here are the list of profiles supported by the version 1.6, the core profile, which is the mandatory profile. Basically handles all the messages which are required for the charging and stop charging, etc. Apart from that, we have the local authorization list message, and which is mainly to authorize when there is no connection between the central system and the charge point because of the network issue of anything. And then the charge point can take action like it can authorize the user if the user has been already authorized and it has the validity tag. Then we have the firmware management profile, which is for the over-the-air update of the firmware for the charge point itself. So we will not see all these profiles, but we limit to the core profile and its messages. Here are the list of the messages which is supported by the core profiles. And again, we are not going to see all of them, but at least we will pick the messages which are essential for one complete charging cycles. So we will have a look into the authorize, boot notification message, meter values, start-stop transaction, and then remote start-stop transactions. Okay, so boot notification is the PDU message, which is the first message which charge point sends to the central system. So central system will enumerate or discovers there is a charge point available in the network using the boot notification message. And after a startup or the reboot, or the charge point initiate the communication with the central system. So the boot notification message carries the following informations like charge point model, charge point vendor IDs, and then the ICC ID, IMSI ID. So no other PDU message should be sent without acknowledgement or of the boot notification or the acceptable of a central system. Okay, when the user wants to get into the access of the charging station, first he has to get authorized. So the unique identifier authorized unique identifier is used for the authorization purpose. This unique identifier is read from the access card using RFID on the charging station. Otherwise, there is other mechanism like when the mobile applications like smartphone mobile application. Otherwise, the web browser is used to kind of a virtual ID directly. It can start communicating with the central system, and then central system will authorize the user. So when the when the user get authorized, then he can able to start charging its vehicle after connecting the connector into the EV from the charging stations. So once we have authorized, the user get authorized, then the charge station, after connecting the cables, the charge station can deliver the power to the electrical vehicle. After that, it can send a message, confirmation message to the central system that start transaction has been already started by sending the start transaction PDU message. Okay, once we have the start of the transaction, then if the battery gets completed, otherwise if user want to interrupt the stop the charging, then he can hit a button on the charging station. Then the charge point can terminate the power supply to the electrical vehicle. After that, it can send a stop transaction PDU message to the central system to notify that a transaction has been already stopped. Okay, so far we have seen the stop transaction and boot notification, all these messages which originate from the charging station to the central system. But there is a way, as I said, when the user wants to start charging, he can request to the central system using the mobile application or the web browser. Then charging station can request start transaction message to the charge point. So this is used by the two messages called the remote start transaction and remote stop transactions. Upon receiving this remote start transaction, stop transaction, charge station can decide whether it can start or stop based on the local environment, like whether the power supply is available to deliver the EV or else the cable is connected. So once it is done, then again it should follow the same process of what we have seen in the previous slides, like start transaction, stop transaction. So one of the peculiar case with here is the remote stop transactions. It is not necessary that these remote start and stop has to be always the pair. Even if the local charge station sends a start transaction, those transactions will be available on the central system. So remote stop transaction message can be sent from the central system for already started a charging session. Okay, there are some cases where malfunction of the cable retentions, like after authorization, the user has to get the cable and then connect to the chargers. If there is any malfunctions happens with that, then he can request the CPU operator, the CPU operator, so that the charge point operator can send the unlock connector message from the central system to the charging station. Okay, so we have seen the start transaction, stop transaction, which has the which carries the informations like which connector it has started, and also at the time of starting, the meter values are sent, and also at the time of stopping, the meter value has to be sent. So based on this stop and start transaction meter values, the billings are generated, how much the power has been consumed. Apart from that, in the start and between the start and stop transactions, so the charge point may collect the information of the current meter readings and also send it to the central system. The purpose is like the central system may have the kind of graph mechanism to plot how much the charging is consumed, and for those purpose, it is the meter values are used, and the meter values carries the values like a connector ID and the current meter value. So it is like frequently sent from the charging station to the central system. So we have seen so far the specifications, what are the basic messages of the predefined unit messages, and these predefined unit messages are not sent to central system directly. Instead, it will be wrapped into or encoded into a wrapper called a remote procedure call messages. This carries a message type and then unique identifier and the payload of the OCPP PDU message itself. So the message type are primarily categorized into three types. One, the call to sender request, and call result is to reply or getting the response for the call message, and then call error if in case of any error or the failure with the reasons. The OCPP specification is mentioned that there should not be a new call message originate either from the charge point or central system unless until the previous call message has been responded or timed out, which means there will be only two call messages exist in between the charge point and the central system at any instance, one originated from the charge point, another originated from the central system. And there should not be new call message should be started before the response or the timed out. So we have seen the message frame, and here we will see the example for the call request message frame and also the call response message frames in details. So we have the message type of 1 byte, which carries constant 2 for the call request, and we have the message ID, which is used for the purpose of identifying the message itself. So it should be the unique identifier of any string of 1 to 32 bytes. After that, the action, which will carry the PDU, what is the purpose of the PDU, like the boot notification or a start transaction or stop transaction. And then the payload itself. The payload, what we have used in this presentation is, there are two types of payloads supported, or PDU message format supported in the OCP 1.6. One is the JSON format, and another one is SOAP. But with the later version or the version 2.0, only we have the JSON format. So throughout these slides, we have used only the JSON format. So here we can see the example for the boot notification, and then the charge point vendor IDs and the models has been sent on the call request. And we will get into the call response as the message type constant 3, and then the unique message identifier, which is used to send for the call request here. The same should be here, so it can match which packet the response has been received. Then we have the response JSONs for the payload for the boot notifications. So we have so far seen what is the specification, what specification has said about the message format and then the message sending the wrapper. But how could we really visualize into the complete charging station? So we will see here one of the example use cases, because we cannot able to cover all of them, but here we have mentioned one of the use cases, like how the user interaction between the EV and the EVSC, and then the EVSC to charging station uses the OCPP PDU messages. The first, the user has to get the access. For that purpose, he shows the access card to the EVSC. Then the EVSC, we will have a card reader like NFC or the RFID reader, which will read the ID tag. Once it read the ID tag, it will send the OCP authorized request message to the central system, and then central system will check all the database, like navigating whether the ID tag is matched and it is already in the valid state, or else it's expired or blocked, and all these states. So once we will take it to the happy path here, like the ID tag has been already matched, and then we will get the response like authorized. So once authorized, the user is able to the connector is released from the EVSC, so user can able to pull in the connector from the EVSC and then connect to the EV. Then once the cable is connected, user can able to press a button of the start button available on the charging station. Once the start button is pressed, EVSC then release the circuit for delivering the energy, and then it can send the OCP message that the start transaction message that transaction has already started with the meter readings when it was about to start. So one successful transaction, then the meter values is continuously sent from the EVSC, like how much consumption by the EV, until the stop transaction or the complete charging cycle ends. So when the user wants to interrupt or stop the charging, then he can hit the button on the stop charging button on the EVSC. Then the EVSC will shut down the power to the EV, and then it can send measure the energy meter, what is the last reading of after shutting down, then it can send the OCP message stop transaction to the central system. After that, cable can be disconnected and inserted to the EVSC. So we have seen one complete charging session use cases for how the user interacts with the charging station directly for the start and stop chargings. We will have another example which showcase here. The user can directly interact with the central system instead of EVSC. So if a user can have a web authorize or the smartphone which can able to interact with the central system, then the virtual RFID is used here to communicate with the central system, and then the central system will check the database and then it will authorize the user. Once he has been authorized, the EVSC will unlock the connector, so the connector can be, the user can pull in the connector and connect to the EV vehicle. After that, the user can start the transaction or the start charging by pressing a button on the application, and it goes to the central system, and then central system will send a message, remote start transaction message. After that, the EV has to solely responsible to decide whether it can deliver the power to the electrical vehicle based on whether the good power is available to that, and also the cable is connected and the proper things of all this. So once charging is started, then it can send a start transaction message to the central system. It carries the same the cycle what we have seen in the previous slides, like it sends meter values frequently. After that, when the user wants to stop, then he can request the central system using a web application or else the mobile phone smart application. Then the central system will send the remote stop transaction. After that, the EVSC will shut down the power and will do the stop charging sequence. After that, it will send a stop transaction PDU message to the central system. And finally, the EVSC or the user can disconnect the EVSC or the cable from the EV and to the can connect back to the EVSC. Okay, so far we have seen how the OCPP specification messages appears and how it has been wrapped into RPC message to communicate with the central system. So now we get into how the protocol is being implemented in the Zephyr RTOS. Since OCPP is application protocols, so it can coexist with the MQTT, CoAP, and other application protocols. The OCPP sends a message using the socket APIs, especially the WebSocket APIs, to the central system in any of the network interface like Ethernet, Wi-Fi, or the modem. And then the OCPP exposes a public API for the application use case, so application can directly use those APIs to send data to the central system or back and forth. Okay, now we will look into how OCPP stack is implemented in the Zephyr routers. So as I said, we have native, at the bottom we have the native WebSocket implementation of the Zephyr, and then in the top we have the application which consumes OCPP consumer APIs. So from the bottom up, we have the RPC message format, and above that we have the JSON PDU format. Then we have the list of profile implementation, the core profile which has the start transaction, stop transactions, and then we have the interesting one which is the key management in the right side. So what is this key management is, we have the key value pair which is maintained or used to communicate between the charging station and central system. If, for example, so we have the meter values, it has to be sent frequently, but how much time it has to send, so this is configurable using the key value pair. Apart from that, we have heartbeat messages, so then timing between the heartbeat, how much time it has to send, it can be read from the central system and also can be changed by from the central system, and for that purpose we have the key value pair. Then we have the OCPP internal implementation which carries the socket connection and the reconnection handlings. So user has nothing to do with the when the internet or the socket get disconnected, the OCPP stack itself can able to reconnect, establish the connection, and we have the user notification handlings. For example, so when the central system sends some of the requests to the charge point, then it has to notify to the user like start charging, stop charging. Otherwise, even the internal request from the OCPP, like the meter value, the frequency has to read from the application, that will be used by the user registered callback in the init functions. Now we will look into the API which is exposed to the consumer. The first one is open charge point, the OCPP_init API, which is supplied with the charge point information and central system information. So, the charge point model, vendor, and the number of connectors are the mandatory information which needs to be filled to the for the charge point information, and then central system information like IP address, which is a resolved one, and then port and WebSocket URLs are supplied here. So before initializing the OCPP library, the network interface should be already up and running, because once we call the OCPP init, then it will try to establish the socket connection with the central system, and then it sends the boot notification message. Then we have the pair of session handling APIs, so OCPP session open and close. So each connector, then the charge point may support n number of connectors, and each connector should have open a new unique session handling before any of the further like start transaction or the stop transaction API is used. The session management is sole purpose of internal to the stack and nothing relevant to the specifications. Okay. So from the application, so when it wants to get authorized, then it can use the OCPP_authorize API, which carries the ID tag as an input, and then we will get the status as a response, and the status may carry the invalid, accepted, blocked, etc. So once we have the response with the OCPP_accepted, then the user is allowed to start charging. So we have this OCPP_start transaction messages, like when charging station has already started delivering the power, it can read the energy meter values, and then it can send the start transaction message to notify that the central system transaction has been started. So it is binded with the connector ID, and then what is the energy meter at the time of start. Then once we have the the transaction has been started, then user callback, the register callback and the init function will be called from the stack using the reason like get meter values, just to read the meter values. So it is recommended that this callback function needs to be written as quick as possible. Like the meter value should not be read from the callback itself, maybe another parallel thread which can read the and can share between the this callback function on another thread. And the other reasons may be like start charging and stop charging, which is originated from the central system. Once the complete charging cycle has completed, then we can use the application may use OCPP_stop transaction with the reading from the energy meter. Okay, we have seen so far the OCPP, which is used primarily between the charge point and the central system. But does EVSE really complete with that? Not really, because we have the real handshaking between the charge point and the electrical vehicle and to deliver the power, which is mentioned by the standard IEC 16851 and ISO 15118. Unfortunately, these specifications or the standards are not open, and we can see very overview about that. So we have two mechanisms for handshaking. One is for the control pilot, and another one is proximity pilot. Control pilot is mainly used for the communication to negotiate the charging level of the car and the charging station, and then proximity serves for the cable detection and current limitation. So OCPP, I would say the OCPP part will cover 40 to 50% of EVSE. The other part is still covered by the application with the IEC implementation. So if you will see the use cases here, once a user got authorized, then it will be in the state of A1, which the control pilot the values is the voltage level is in the 12. After that, the cable is connected to the EV, then it will drops to the 9 voltage. By detecting the cable is connected, then the EVSE can prepare for the charging, and it will communicate to, or it will notify the electrical vehicle that the charging is it is ready to power the charging, deliver the charging. So the PWM signal is used with the 9 voltage. After detecting the PW signal by the EV, then the EV will pull down the control pilot voltage to the 6 voltage. So the charging is started, and then we have the we can send the start charging OCPP, and then we have the EVSE stopped once we get full charging, and we will enter into the state like C1 and stop charging. So once the user presses the stop button, it can come into the default state, the B1, and then the cable can be disconnected, so it will go to the state A1 or 12. Okay. So we are almost come to the end of the presentation. Here the state like the OCPP is currently under review, and it will be get merged after a review is completed. Then currently we have 1.6 core profile is supported, and then the future work is the TLS support and 1.6 optional profile and 2.0.1 supports. Thank you. Do you have any questions?
Yeah, 1 second.
Hi, thank you for the presentation. This was really clear to me. The diagrams really helped in terms of explaining each of the steps and in order for this overall charging workflow. Okay. One thing that perhaps isn't so apparent is really this start transaction phase, right, whereby the charge point equipment sends this request to the central system. So is this a required step in order for the vehicle to begin charging, or is this purely to send some information to the central system to like notify them?
Okay.
Is this a critical part, or is this a blocking operation, or is this like sort of?
Okay. Yeah. So the main purpose of OCPP is, as I said, it has to communicate to the central system so that central system know how much the power has been consumed by the user, and then it will generate the billings. So for that, the start transaction should be notified to the central system, and then also the stop transaction has to be notified to the central system with the meter values. So it can the central system will calculate based on how much the start of the energy meter and what is the end value of the energy meter, and based on the difference, it will translate into the billings.
Okay, thank you for clarifying.
Hello, very good presentation, and I would like to extend your topic about ISO 15118 a little bit.
Yep.
So that standard is more about encryption safety, and one major part of it is plug and play.
Okay.
So yeah, but I don't see any content on your slides, and I'm curious about does your company support such a feature? And when we do plug and play, we find which is so difficulty to connect your charge point to the vehicle. So you have to let your charger to notice who is using it, and which account it belongs to, and when to start chargers. So by that standard, the ISO 15118 provides a very complicated handshaking certification procedure there. So how does Saver helps you on it, or doesn't help at all?
Okay.
Thank you.
So since it is a closed source, we cannot able to explain much into the current presentation. Otherwise, we have implemented to one of the customer the EV with full blown with a specification of 11518. Yes. Is that answers your question?
I think it's more than that, but I can contact you with you later.
Sure. Thank you.
Okay. Thank you very much.
Oh,
yeah.
there is one
There's
more.
one more.
Yeah.
Yeah. Sorry. I didn't.
Hey, I was just wondering, how often does the meter pull back to the central system, and also what happens if you miss the stop transaction from the central system? I don't want to end up like getting free energy from this charge point for forever, but I was just curious how OPP or OCPP handles that.
Okay. For your first question, it is configurable values that how often the meter value has to be sent. As I said, there is a key value pair which is read from the central system, and also it can modify the values. So based on that, the meter values is being sent. And regarding the last question, it's stop transaction has been missed by the central system, you mean, or? Because the
No, if
stop
the charge point misses the stop transaction from the central system.
Okay, so central system does not send a stop transaction message to the charge point. The charge point is the one which will notify the central system that transaction has been ended with a stop transaction message.
Got it.
Okay.
Thank you very much.
Thank you.
Recording in progress.
Test, test. Test, test, test. Sounds good to me.
Checkity check. All right. All right, how you guys doing? Can you hear me okay? So my name is Jason Shepard, so I'm CEO of Atom, and this is my partner in crime, Steven. He's our CTO, and so today we're going to talk about a new project that we're donating code to Linux Foundation to seed, this Project Ochre, and we'll kind of walk through what it's all about. I kind of come at things from the IT side of the house. I was at Dell, and there was a company called Zadita that I was at most recently. We're like mini-me Zadita, and we'll kind of talk through how all that plays out. But I've been doing this for a while, past 10 years, have a lot of experience in open source, have launched several open source projects in Linux Foundation, chaired boards, and stuff like that. So this is kind of the next step as we see more and more compute going out into the field and kind of provide some context around that. But quick intro.
And so Steve Bart, a CTO. I mostly from both the software and an IT background. Started my career at a company called APC where we did a lot of data center equipment, managing things over the network. Weren't calling it IoT at the time, but it is a lot of the same concepts. Went through that, did some time at Microsoft, and then ended up at Schneider Electric in France, where I worked a lot on their internal IoT platform called EcoStruxure. So built a lot of things, saw a lot of problems in this space. Part of the challenges that I always saw in our team was the device side of things. It always taken a lot longer to develop, very difficult. Our cloud team got to move a lot faster, and the embedded team was always sort of the long pole in the schedule. And so that's something that we're pretty passionate about, and we're going to talk a little bit about how we help address that and make it easier for everyone.
Cool, and we literally launched the company. We've been around for a little bit, but yeah October, November, but publicly,
so,
pretty much this week. But so you guys know the drill with embedded. I mean, a lot of this is when we're pitching to folks that don't know embedded, the challenges, and you guys have the skill sets. But there's a lot more people out there that don't know how to program embedded, don't know C. I know AI, I know I'm doing IoT, I'm programming in Rust or whatever. And of course, there's a lot of stuff kind of converging even with the likes of Rust, in this space. But it's difficult. And the lock-in of silicon and it's kind of the opposite of how we've been developing things in the cloud for some time, necessarily. But these devices, as we all know, they're getting more and more capable. We're starting to see more intelligence being put into them. Clearly, security challenges are on the rise. And then also, like the people that know about, AI for vision, quality control in a factory are not the people that know necessarily how to program to an embedded device, or this person that knows about security or whatever. So bringing things together with different skill sets is difficult, especially, and in the embedded sense. And then, of course, just more and more in general, compute happening on these devices, and we're seeing SBOM. There's new regulations around memory safe code that are popping up, or at least guidance around memory safe code, and all of these factors are, we believe, are necessitating a modernizing how we approach embedded. And of course, we picked Zephyr for a reason because it's a modern approach in general, but we're kind of building on top of it. So we joke at the company that the 90s called and want their tools back. We've seen a lot of change in the cloud over the years. Embedded, obviously there's been things that have happened in the embedded space, and Zephyr, again, is we think a really important step forward in a modern architecture. But embedded today, predominantly, it's kind of like, for embedded devices, it's kind of like server development was before VMware came along. And then, of course, you see Docker and Kubernetes and all that kind of stuff, functions as a service, and all of that evolution. As the cloud grew, now there's all this talk about edge computing and processing being more distributed because you can't send everything to a central data center. We're seeing a lot of these technologies now come back out into the field, but there's a practical limit to how far the cloud technologies can come as they are today. And clearly, WebAssembly has become very hot in the cloud native space, coming out of the browser. But we're seeing a bunch of activity in CNCF, and the Docker crew is talking about it, and a variety of things. But if you look at the continuum, this is a taxonomy from LF Edge. If you look at the edge as a continuum, well, first off, a lot of people say edge, and it's a misnomer. They're just confusing people. It's like, what's the edge? Well, what is it? people are like, what's the near edge and the far edge, which is funny because the telco would say near edge and far edge, but it's opposite of what you would think as a user, near edge, far edge, or thin edge, thick edge, and all this stuff. So the taxonomy that we did in LF Edge, this was like around 2020 timeframe, breaks it down into inherent technical trade-offs. And if you look at the continuum, the summary is I'm either in a distributed but still physical data center, regional data center, metro data center, on-prem data center. So I have a defined network perimeter. It's physically secure, and I can run Linux and Docker and Kubernetes and all that. Doesn't matter what the servers look like. It's just I have those tool sets. The next step down as you get into the smart device edge, as we defined it, was I'm out of a traditional data center, but I can still run Linux and Docker and Kubernetes and stuff. So I have to have a unique security model or zero trust security model. I have to assume I'm going to lose connection over times and stuff like that, and the like. So that's the next click down. And then the final click down is I'm out of the data center, I'm out in the wild, I'm basically embedded, and I cannot run Linux. I don't have the memory for it. So that's what we call the Linux barrier is it's generally, take like Docker with Linux, 512 megabytes of memory, maybe 256 is kind of like that lower limit on a single node. We're talking, of course, in this case, kilobytes of memory. So if you look at all the different technologies on here, like a Kubernetes, I was previously at Zadita. Zadita uses EOSS from LF Edge, so this Ochre will be a project right next to it. Even virtual machine projects like Zen and all that. All of these different tools are shifting left in the continuum, but there is that hard stop. They cannot go past the Linux barrier. What we're doing with Ochre is we're taking WebAssembly, which happens to be a really thin, lightweight, secure virtualization technology that of course started in the browser and then has been making its way into cloud tools. It actually provides those cloud-native benefits and extends past that barrier. So by combining Zephyr and WebAssembly, and we'll talk a lot more detail around the architecture, this project basically gives you the feel of developing for the cloud with OCI-like containers without having, but doing it on very, very constrained devices. So, so Ochre, it's not really an acronym, but it is Open Container Runtime for Embedded. It also happens to be it's a color, but then Stevens lives in France, and this is the French spelling of the color.
The acronym worked a little bit better. There's an H in the English spelling, so we couldn't figure out how to make H work.
So I'll have you get into more detail. I'll kind of give the high level. So this is a thin shim that sets up an environment to run containers in. An Ochre container, think of it as like Docker on a diet. So very lightweight containers that can be written in any programming language. You could take existing C code, lift it, and shift it up on top of the Zephyr runtime in a container, but then write new things in Rust or Go or whatever. 256K, of footprint. We'll talk more about performance as we go, but. So it really feels like cloud native, like your containers can sit in the same registries as a Docker container. It's really sort of approaching embedded from a cloud down mindset, and then you talk through all the the abstraction and whatnot. But so Ochre is that runtime. As we talk through it, we are donating this to LF Edge, so part of the Linux Foundation overall umbrella. Within the next couple months. And so we look forward to having folks be able to collaborate on it. The goal here is to make these containers kind of the equivalent of Docker for the embedded world. So with that, I'll hand it off to you to get into details.
So, why containers? What's wrong with traditional embedded? And I think I'll start first and say, we don't think that this is appropriate for all traditional embedded. Things like your airbag and really safety critical systems, right? You're not going to want those containers. They're very different types of real-time systems. But there's a lot of embedded devices out there where this makes a lot of sense, right? And if you look at why would somebody use one of these devices, like I have here, which I know you can't see because of the way the podium is, but we'll show a photo in a few minutes. A lot of it has to do with cost. These things, are very cost effective. Moore's law has blessed them just as much as your PCs, right? So the power on these things is pretty impressive. But again, there's a number of these constraints that make it difficult. So on the right side, you have traditional embedded. Generally, this is everything linked together, generally all done in a single build. Usually in one image. Sometimes you might have a bootloader and a couple of loadable modules. I know we went to a talk earlier in this conference where we're doing some dynamic linking, which is pretty exciting technology. But in general, it's all linked together, right? So I need the source code. It needs to build with the same tool stack. I need to synchronize all that. Now, there's a couple core problems with that. First, all the IP, you have to have all the source code. So the IP is hard to keep separate, right? So if you're licensing code from a third party, you have to get that source license. In the open source world, that's not as big of a problem, but for some of the commercial stuff, for some of the other use cases, that does pose a problem. But also, because you have to bring everybody else's source code together, you need to make sure that you can compile it. And sometimes somebody's using a slightly different version of the compiler toolchain than you are. And when you try to integrate those, you run into weird problems, different library versions, different toolset versions. And that just creates a lot of different friction. And again, you're also linking it into effectively a very, very large single image. So whenever there is even like a single line security fix, for example, you have to rebuild and relink everything, which means you have to retest everything, right? So there's this big bang integration. You got to make that happen. And we can solve that with CI/CD, but you still have to test that, right? Provided you're being a responsible company doing the proper things to release software properly. And that's a huge amount of time. And then when you deliver that, you have to deliver that entire payload of bits to the device, which could cost money if you're on a metered connection, could be more risky because you're more time in the air. Some of these devices don't have enough space to store 2 copies of the firmware, so you're literally overwriting itself in there, so they can be really risky things. And what we've seen, I've seen it in industry, I've seen it with customers we talk to, is people are very hesitant to update the devices because there's that inherent risk. And so it's sort of the opposite of what we want to have happen. We want to be really responsive to security. We went to a security talk today about what we're doing with Zephyr and being responsive and doing security reviews and stuff like that. Part of that is patching. But if it's risky to update those devices, people are really not going to go do that. So that's a huge problem with traditional embedded. That's sort of the negative part about that, but the other positive is if I can update the device, I can make it also much more software defined, right? The example everybody loves to use is Tesla. The features of the car evolve the longer you have it, which is not what you normally have with cars, right? So to be able to do this with these devices and have the devices improve over time, be more adaptive, and increase those features requires updates. And if updates are risky, people aren't going to do it, and then you lose that business agility. So anyway, that's traditional embedded, and there's nothing wrong with that. There's just a couple of sort of realities that you have to deal with. If you look on the left, that's more like what you would see in a cloud-native application, right? You have an application broken into much smaller chunks, containerized, so these things are isolated. That allows you to put all those things into these neat little buckets that are much smaller, much easier to develop by a small team. And again, going back to that security, one-line security fix, there's a good chance it's probably only in one container, which means you only have to rebuild that one container, retest that one container. Obviously, you have to test it with everything else. But you have to do much less testing, and then you can update just that container. And if you look at how we do this in the cloud, we generally will do that live. We don't have to reboot the device, which is something you generally have to do with a firmware update. Also, if you're making these, if you're designing this to be much more modular, you can use the containers as a unit of modularity, which means you can then reuse those containers in different applications. So you can now actually do reuse because you're building these containers that have much more limited functionality. And again, you get a lot of those same benefits of I don't have to retest it, I don't have to do that. I can compose my application versus having to build everything and link everything from scratch. The other thing, though, is to enable that, you need a runtime, right? So if you look at what is done in OCI container, Docker container land, there's a bunch of supporting infrastructure around how that works. And when you start looking at things like Kubernetes, there's even other services there. So things like hardware abstraction, service location, container communications. Those are things that we provide in the Yoga runtime, and I'll talk about those on the next slide. So what does our architecture look like? As Jason said, we're based on Zephyr. We're technically RTOS agnostic, but we chose Zephyr for a lot of really good reasons. And we're really starting to take advantage of a lot of those. The biggest thing that we started looking at Zephyr for is the amount of board support that we had. It's very easy to get, tons, I think we're up to like 575 boards. Then you have things like the device tree and device tree overlays, which makes it really easy to say, hey, I have a board like this, but my sensors are mapped this way, right? So we're taking advantage of that underneath because that allows us to support a lot of this hardware. The other thing that Zephyr provides is a nice driver infrastructure, right? So you have a lot of I would say a lot of the same sort of concepts or abstractions that you have in a large operating system like Linux or Windows or Mac OS, but you have that in Zephyr, right? So there's good class drivers, for example, for various different devices. And now I can go and open that device, and how it's mapped to I2C or SPI or UART or whatever below can change, right? In fact, the part can change, right? So if I'm using an air quality sensor or a temperature sensor or a vibration sensor, how I use the sensor from the application perspective has this nice abstraction, and Zephyr gives us that. And then the actual underneath can be done with things like device tree support and the drivers behind that. On top of that, Jason mentioned WebAssembly. How many folks are familiar with WebAssembly? Cool. It's pretty confusing because it's probably not the best name for the technology. It's neither web nor assembly. It's kind of how I like to joke about it. It's basically a very lightweight virtual machine. It's the other thing I joke about is it's basically what Java promised 35 years ago, but actually delivered, right? So it's a lot of those promises. It actually runs on embedded devices nicely, right? But more importantly, it provides a true virtualization option here. And so we're using that as the core of our container runtime. So what runs in a container is WebAssembly code. Little star, we'll talk about that in a second. And that allows us to basically have code that can run across any architecture. So we can run on x86, because we can actually run on a simulator here with Zephyr. We can run on a board. I'll show this later. This is an ARM Cortex M4. We can run on ESP32, RISC-V, anything that's supported by that. There's a lot of wide support. And so that same container now can run across all of those, which is quite an interesting thing. So we have those two things. We have the base on the bottom, and then we have the container runtime. And that's good. That's like, now I can boot up on the device and I can run code. But that's not really a container runtime, right? That's just running stuff in a virtual machine. And so if you look at, again, how that journey of the cloud happened, it was when we started getting things like Docker and then some of the tools like Vagrant and then suddenly things like Kubernetes that allowed us to manage this and orchestrate this and do it at scale. So that's what really Ochre is. It's taking those two technologies and building the rest of that out to create a real container solution. One of the developers on our team really challenged me early on, and we're like, is that really a container? And so we had to actually have a lot of internal debates about like, what is a container? And what does it, like what's enough of those properties in the embedded space to legitimately call it a container? And so I think, actually I'll jump to that, since I brought that up. We've actually done the comparison of that because I was really challenged by one of the internal developers, and he was right. We really need to look at that. It's not just running code in some runtime. It actually needs to be something a little bit more than that. So in this chart, you'll see the two sides. I broke it down to sort of the normal things you'd see: compute, storage, networking, and security. So from the compute perspective, things run in a WebAssembly runtime. So that means it has to the build target is WASM or WebAssembly. Things are packaged as today they're packaged as a WASM module. That may change in the future as WASM and WASI kind of progress through the standards. But today we run a single module inside a single runtime instance. And then we schedule that behind the scenes with native threads. And we do have the ability now, but we will be extending that a little bit more to actually have multiple threads within the same container, right? Those will also be OS threads. If you look at what happens on the OCI container side, you have platform-specific code. It's compiled for a particular architecture. We have some fancy magic in OCI land for allowing to have multiple architecture containers, but that's really just a easy way to have multiple versions of the same container and reference it with the same label. And behind the scenes, it picks the right one of those. In our case, our code can run across all of those because WebAssembly provides that virtualization layer. And again, Jason was talking a lot about the Linux barrier. For containers to work and for compute to work, they're essentially processes, but they're walled off with things like namespaces and C groups and things of that nature. But they're run on that shared kernel. When you look at how their executables are packaged, it's basically a tar file system that gets expanded. Obviously, that's not going to work on an embedded device, which is why we're using the WASM modules. When you start looking at the other parts of the container, right? So that's the compute, that's the me running code and doing interesting stuff. But to support that code, you need things like storage, and you need networking, you need security. And what we did is we looked at what you can do with an OCI container and said, hey, that's interesting. It needs to be conceptually similar, but the implementation of that is probably not going to be, it probably can't be exactly the same. And so when you start looking at things like storage, well, on the OCI container spec side, you have things like this union file system, right? We expand all these tar files, and you have layers, and some of them are writable, some of them are not, and it's really complicated, and it takes up actually a lot of resources, and obviously that's not appropriate. However, the ability to have things like, I have an ML model that I need to load dynamically, and that needs to come down with my container, right? So I need to be able to reference that object, right? So we have the ability to have a very small simulated file system. So we're using a little FS for that kind of stuff. And also have things like blobs. So we can have binary objects in there. Those could be images, they could be ML models, they could be, firmware images for downstream devices or other daughter chips and things of that nature, right? So we have the ability to reference those. Now, you're not going to get the full POSIX permissions and all that other stuff, because that's not appropriate in that space. On the networking side, again, the OCI containers, they're equally complicated, right? There's a whole virtual networking and network address translation and a lot of complexities. Actually, there's a lot of different options in there, and I still don't get my head around all of them. But massively flexible, but also lots of overhead, right? So even to just do NAT between two containers on this kind of device is probably going to take up way too many resources. But the reason why those exist is for us to access outside network resources and to communicate between containers, right? And so those things we thought were the most important parts of that. So what we've built on our side is the ability to have marshaled sockets. So you can open up a socket with a standard socket call, make outbound connections, even open up server ports and listen. And then also we have a way to do inter-container messaging. So very simple, almost like MQTT, but it's all done through a messaging API. So that allows, and we'll actually show a demo in a little while about this, but that allows one container to go pull data, pull something from a sensor, so go read a value, maybe do some hysteresis and debouncing and some data processing there, and then pass that off to another container that's going to do analytics, right? And so you can kind of build these pipelines of really useful things, just like you would do in the cloud with a microservice architecture. So again, that networking allows these containers to collaborate. And then from a security perspective, okay, on the OCI container spec side, you're looking at Linux, and there's a lot of things you can do. There's a lot of best practices. There's a lot of tools that are built on top of OCI and Docker and Kubernetes to do that. You have OS level protection in there as well. On the other side, in embedded, you generally don't have that, right? We're lucky to have, we have threads. We don't even have sort of process boundaries in a lot of cases. Some of these platforms have memory protection. Many don't. So when we started looking at it, well, what can we do? So the nice thing about having WebAssembly as a runtime is that gives us a nice security boundary, right? WebAssembly has this really good property of nothing can really escape outside of that container, right? So by default, if I just spin up a runtime for WebAssembly, I can do loops and math and comparisons, but I can't access the file system. I can't access the network. I can't do this. And this is true in the browser. This is true on our embedded platform as well. The way you make that useful is you inject interfaces into it. You inject these APIs that are then available in there for that container to call, all right? So for example, we can inject an API to open up a socket, right? But that call is marshaled by our runtime. So what that allows us to do is it allows us to have security controls over that, right? And so we can actually, in our container manifest, say, hey, the code in this container can access the file system, can access the network, right? But if it tries to go do something else, we'll block that call, right? So if it opens up a socket, yes, you have the permission, you allow that to happen. And so when you look at things from a security perspective, it makes it easier to build defense in depth, for example, into your design that into your product, right? Because you now can say, hey, this thing can access the network, this can't. This can access storage, but these can't. The other thing that we can do is, just like in big OCI containers, we can do image validation. So I pushed code down. I know, Cedric, in your presentation, there was a question about hey, if I can dynamically put code on this device, I could dynamically put bad code on this device. And how do I ensure that that happens? And so if you look at how that's done in the Docker world, they use digital signatures and certificates and cryptography to say, hey, you can only run code that's signed by this particular certificate. And we can do something similar here as well. Let me go into performance, and then I'll probably jump into demo because I think it's interesting.
Yeah, we got 15.
15? Perfect. So I go through this presentation, a lot of folks are like, that's great, but you're running a virtual machine on an embedded device. The performance must be terrible. The truth is, it's actually not that terrible, right? For normal interpreted WebAssembly code, we're about 5-10 times slower, right? Which sounds horrible, but that's for really CPU-bound code. If you're writing an application that's reading from a sensor, doing some simple analytics, maybe doing some data conversion and sending a stream of data up, which is kind of common in, say, a condition monitoring industrial application, the performance delta between those two is going to be very, very minimal. Now, that said, we weren't really happy with that level of performance degradation. For a lot of applications, especially when you're talking about AI and ML, that even a 5x hit, it's untenable, right? It's not gonna be something that will meet the performance requirements, right? Or somebody will have to buy a much more expensive board that has a lot more CPU power, and now you're in that class of closer and closer to Linux-capable devices. So what we've done on our side, and this is part of the Atom commercial product, is we have the ability to do ahead-of-time compilation. Because we know the CPU architecture that we're deploying to, we can actually take the WebAssembly and do ahead-of-time compilation. And that gets us to darn near close to native performance, because it literally is native code. So slight overhead on that, but for hard CPU-bound applications, it's like a 20% slowdown, right? So we think that that's really, really good on the performance side of things. We also have the ability to run absolutely native code. And so for things that really need to be accelerated, things like neural networks and some of the AI stuff, there is standards within the WebAssembly world. Example of that is called WASI-NN. Dan from Sony Midicor talked about that. That allows you to have an API and then have all completely native optimized accelerated code underneath. So we do have that as well, if for those applications that truly need that last little bit of performance out of there. The other question people have is like, that's great, but these containers must be big. They must be, they must have some other overhead. They're actually incredibly small. So I'll show you a couple of different applications today, but our smallest individual app is about 300 bytes. Not kilobytes, actual like 300 bytes. And I was actually doing this demo before, and I was like, why is this 1,000 bytes? It turns out that I was printing a very large string. And so the 1,000 bytes was actually the data in there, right? So the overhead of this is pretty low. And the reason for that is a lot of the common code that you would normally call, like libc and all those other functions, are in the runtime. They're part of Zephyr, right? So we don't have to link to those, right? So we just have effectively the code that somebody's writing in there. A few tricks we have to play with the compiler to sort of say, hey, don't link in libc, don't do this, and do some optimizations. But we literally can get this down to about 300 bytes. And I've done this in both C and I've done this in Golang as well. Not done this in Rust yet, because I'm still learning to understand Rust. So, let's see, anything I missed on that? And I mentioned before, we can run this on pretty much any processing architecture. ARM, we can run on something as small as a Cortex M3. We run really well on M4 and M7. We can run on Tensilica, so the ESP32 platform, which is an amazing platform for the cost. We can run on x86, so you can actually run our runtime on a PC, so you can actually do development on the PC without the hardware and have all that simulated, do some debugging and whatnot. And we can also run on RISC-V.
And actually, one of the questions we get often is when does the relevance stop as you look at the continuum from, we're making it possible to run containers on lightweight devices. When does it stop? But we're not trying to be, Docker or Kubernetes or whatnot with this project, but if you bleed up a little bit, well, I just gave you 256, 512 megabytes of memory to do something else with, where that costs you money on your BOM or whatnot. So we do believe there's going to be some bleed, but it is optimized for this class of device.
Yeah, there's like the Raspberry Pis of the world, which are quite literally faster than like mainframes when I studied in university, right? They're pretty like little mini supercomputers, right? Compared to these devices. But there's a set of application level chips out there, that are Linux capable, that have some of those resources, but as you say, just don't, they kind of fall in that space where that's just not enough to do the kind of things you want to do on that. And so our stack is being as small as it is, gives you a lot more headroom there. And I think that's pretty, it's going to be a really interesting space for some of those applications. And yeah, I talked through this before. I don't think I need to go through this. This is mostly about WebAssembly. The one thing I'll say today is there's a lot of work going on in well, it's a little bit confusing. There's WebAssembly, which is the runtime in general. That's the language, the virtualization. That originally started in the browser, and that still has a lot, that's where a lot of that comes from. There's a subgroup called the WebAssembly System Interface, or WASI for short, and that's where a lot of the work outside of the browser is happening, right? So you hear the likes of Cosmonic and Fermyon, and I can't remember all the names, but there's a lot of them out there that are building things that run on server class hardware, but are running that runtime, that WASM runtime outside of the browser. It's sort of the distinction between, say, JavaScript and Node.js, right? In that WebAssembly group, it's very, very active. There's a lot of work to go on about, like, what is the platform? What should the platform that is WebAssembly outside the browser, what should that look like, right? What calls should be available? How do we structure that? And so we're part of that community. We're working really closely with that. In fact, we're working on an embedded special interest group within that to define how does this platform look like? What does that platform look like? And so some really interesting things going on there. It's an active space, so if you want to get involved, we'd love to have participation there. Okay, with that said, I'm going to jump to the demo. And unfortunately, you really can't see. So that is over here. It's at an angle, and it's a little bit difficult to see. But I'm going to run through a couple of different demos here, showing you some of the capabilities, the typical Hello World app, but then I'll show you something more interesting. The setup we have here, the green board is a Nordic Semiconductor NRF 5340, so it's a Cortex M4. I think this one has 384K of memory and about 2 mega flash, something like that. The board you see on the bottom, this one here, with the red LED, that's actually the modem. This board for this particular dev kit doesn't have Wi-Fi, so that's the Wi-Fi chip. And then the purple board next to it is a proximity sensor. So let's go and, oops, I'll give you the summary. Let's go show you a demo. Okay. And that is readable. Excellent. All right. So this is our platform booting. So obviously you see the Zephyr OS. You see that the Okra project started. And again, I mentioned before, we know what the target is. So that allows us to do optimizations in our commercial product at Atom. We understand that, and we can optimize things in the cloud because we know that target. And then you see the runtime started. So right now, this device has no application assigned to it. And if the network gods are kind to me today, we can go deploy something. One of the things that we tried to do is, again, we're trying to do containers on microcontrollers. And people already understand, they already have a mental model of what containers are. So we want this to be as similar as possible. Obviously, the implementation details aren't the same, but we want commands to be very similar. So here we're using our Atom tooling. So I'm just going to say Atom run, just like you would do Docker run. And then I have a container called Hello World on latest. And the only thing different, and so normally this is what you would do with a Docker container. But in this case, I have to actually tell it what device to do. And this one's surprisingly called device 2. Right? So that's going to go out there. What you'll see is periodically the management agent on our platform, again, if the networking is working, will pick up the fact that there has been an update and automatically download it. I am cheating, just to be careful. I've pre-downloaded the apps for this demo just because I didn't know if I'd have good connectivity. So it's actually getting this from the cloud, but the images are not downloading live. We can do that later if you want. So as you can see, this is just the Hello World app that we have, right? So you'll see that it found that there's something to download, and then our entry point for our containers is this method that you have to expose called oninit. We can look at some of that code later. And so this is just doing a bunch of printfs. Again, nothing all that exciting. But one of the interesting things is, as Jason said, one of the cool things in the cloud is to have, with containers and cloud native, is to be able to use the right tools for the right job, right? If I'm writing network services, maybe I want to do that in Go. If I want to do AI and machine learning, I'm probably going to do Python and some other, PyTorch and things of that nature. So let's do something interesting, right? Let's run this Hello World app, but let's do it in Go. And so this is similar to the other one. Sorry, I should give it a little bit more fanfare, but Hello Embedded Source Summit, right, written in Go. And so this is exactly the same kind of printf, but actually done in Go. And we're using standard Go toolkits here, so there's no weird stack. That's another advantage of us using WebAssembly. We don't have to build the tool chains. We don't have to build a compiler stack. We do have to sort of tune it a little bit in towards like what our compiler flags are. Like, so for example, to get this down to be as small as it is, we're using TinyGo instead of Go. And we're also disabling the garbage collector, because in this case, we actually don't need the garbage collector. So that allows us to get that down. But that's the standard TinyGo compiler. You can go get that from the TinyGo folks. And you can do the same thing with Rust. Rust supports this out of the box, so you don't need to do any of this. Not the most interesting app, so let's do something a little bit more fun. So here, I'm going to run this thing called the proximity demo. And I got to tell it to run on my device. What this one does is it reads from the sensor periodically, and then it prints out both the distance that the distance sensor is indicating, and then some little bars so you can kind of see that. Okay, and so it's not done anything. So as I get closer to this sensor, you'll see it suddenly, right? And so this is really interesting because I'm doing all this code from within the container, and it's calling out through our runtime to a Marshall call and then going down into the driver stack of Zephyr, right? So that's not just hello world in a container and I'm running that and it's not talking to anything in real hardware, right? So I can do that. Okay, so that's that. All of these have been single container demos. So I'm running a container and then I'm replacing that container. You might have noticed that I didn't actually have to reboot. I can do this live, which is kind of interesting. In the real world, you may not want to do that, right? There may be some synchronization you might need. You may need to want to start the container up in a particular fashion. So you may not choose to do that, but you actually have the ability to go do that, right? And I'll show you something interesting in a second. Actually, sorry, I have a script for this. Okay, so here I'm going to deploy a multi-container app. This will take a couple of seconds to run. So what we're doing here is we have 3 containers. So we have one container that's reading from the sensor, called the sensor service. We have an analytics service, which is doing a very simple analytics, it's doing thresholding. And then we have an alerting service, which is doing that, and so which is responding to those analytics. And so in each of those cases, we actually are sending messages between them. So the sensor service is reading from the sensor, getting a valid reading, passing that reading over basically a queue to the analytics service, which is then doing its thing, and then only then is it sending alerts to the alert service. In this case, the alert service is just printing that to the screen so we can actually see what it's doing. But in the real world, you might, this is a proximity thing, so it might be if I get too close, it might shut the machine down, right? If you've seen big, large machinery, a lot of times there's sensors with proximity sensors where if you stick your hand in the machine, it could get cut off, and so the machine will automatically stop, so it'll detect that. So that's the kind of thing you could do with this. In this case, I'm just printing something out. So the demo gods are coming to me. You can see, right, it's telling me I'm too close. But the really interesting thing is there's actually a bug here, which I didn't do on purpose, but then when I discovered I had a bug, I thought it would be a better part of the demo. So the way this is supposed to work is it's supposed to say warning when I get near it. And come on. All right. But it's actually saying critical. And then if I get really close, it's supposed to say critical. Right? So I have the logic backwards. Well, that's dumb. So let's go fix that. So in this case, I'm just going to update that code, right? So the other 2 containers are the same. I just fixed my bug in my container, in my middle container, and now the app is restarted. Now it should say warning, and then critical. Right? So it's like super sensitive to. I probably should have picked one that had a bigger throw on it, but all right. So anyway, that's multiple containers, talking to real sensors, and doing some actual work on that. I think that's it. Actually, there's one other one, since I have probably another 2 minutes. Actually, yeah, let me do this one. Run. Okay, so this one I'll actually have to download, because I didn't pre-download this, since I actually got the network working. So you'll see in a second, it'll detect that there's an update. I think it's like every 10 or 15 seconds it'll check in. Okay, so it's starting to download that, right? So it is now in the background updating this, but at the same time, this application is continuing to run, right? And you'll see that it just exited, and so now this new app is going to take over, and it just blinks the LED, right? Every 5 seconds or so, right? So you can see we can actually do that live, and we can change that dynamically. You can unload and reload. So anyway, that's that. Let's go back to the present. Oops, hold on. I gotta go back to our presentation. Yeah, I gotta find this button. I knew I'd do that. Sorry. I don't know why I had to do that, didn't I? Come on. All right, I can't see that screen. Sorry. Yeah, no, I got it. No, actually, no, you went to, right there. Perfect. Sorry, I can't, I have a different screen. So anyway, Ochre is our container runtime. It's tiny. It's designed for this class of devices, right? We're talking, as Jason said, something that's 1,000 to 2,000 times smaller than, you're. Oh, hold on. I don't know why it's not doing the. Hello? Is it not? Is it not over there? Oh, I know what happened. Yeah, there we go. There we go. You know, I should have used Linux, not Windows, at an open source conference. All right, so anyway, in summary, Ochre is tiny. It's designed to run in these devices. So we're talking 1,000 to 2,000 times slower than what you would, smaller than what you would need for Linux and Docker. We're using a lot of open source technology as our core underneath, and then we're building that framework that allows us to have a true container and satisfy the challenge for my developer. We're going to be dropping code somewhere in the June timeframe, maybe sooner. And then obviously stay tuned for more details. But we're looking for people to get involved in the project. We're looking for people to contribute. We're looking for people to use this and provide feedback and all that. For the moment, you can send us an email at info@atym.io. We'll add you to the mailing list, and then we're in the process of getting the project website up, the wiki, and then obviously the code drop. And so once that's done, we'll add you to our mailing list, and we'll go from there.
Yeah, even before the June timeframe, we'll have the structure set up within Linux Foundation and whatnot. So that's for like right now if you're interested in learning more. But we'll get the structure set up, and then the code will be in there shortly thereafter. And we're working on tying this to the special interest group and the WASI community. Of course, we want to collaborate closely with Zephyr, but this is really about kind of taking a new approach and opening up embedded, we think, to a lot of new developers that don't have the skills that a lot of you guys have. So do new things on these types of devices.
Perfect. And then, oops.
Cool. I don't know if we have, I think we're over. Do we have time for questions?
1 minute.
1 minute.
Do you have any questions? And then we can always go outside. Oh, I think it's on. Just.
Yeah, thank you. This looks wonderful. What's the memory management model for this? Like, how do you constrain the memory that these applications will be using?
So there's the answer that is today, and then the answer that we're going to be marching towards. Today, there's a fixed amount of memory that's allocated per WebAssembly instance. when we create a container, we create a WebAssembly instance. So when we're running 3 containers, we actually have 3 different instances of that. Each has its own address space. Today that's fixed. It's actually a compile time thing that we can put in there. So we can sort of tune it a little bit. Where we want to go in the future is in our container manifest, we want to have the ability to say, I need about this much memory, right? And then we can dynamically do that. The runtime we are using, the WebAssembly micro runtime, does support some of that. It just doesn't do it quite as dynamically as we need to yet, at least in our runtime. So we're going to make that so that it can be tunable. Part of the other thing we want to do as well is provide some analysis tools to kind of give you some guidance as to what should it be. And fortunately, there's a lot of work going on in the WASI groups around how much memory do we have to allocate, right? So the folks that are doing this on the server want to pack a lot of that into a small container. So they have exactly the same problem, but it's a different order of magnitude, but they're trying to do that as well. So we'll be able to take advantage of that tooling. So,
cool. Thank you very much.
Any other questions?
Oh, did you have a? Oh, go ahead. No, go ahead. I was just curious if the like interface from your host telling a container to run is the only interface, or if there's an interface from the other side. If suppose I wanted to have my application launch containers and approach it from within the Zephyr side of things.
That is exactly why we want to have a community open source project for those kind of things. So actually, it's not difficult for us to expose that. We probably want to put some security around that so they could be a really good vector for attack. But in principle, calling an API that allows you to run another container is something that's pretty straightforward and easy for us to do. And we would just have to create an API for that, and then obviously the implementation behind that. One thing I didn't talk about, though, is actually with the sensor service, the container's not running most of the time. It's not just sitting there running in a loop. I have an interrupt and a callback. So I can say, hey, because we have a nice sensor API in Zephyr, I can say, hey, when that signals, call this API. And so our sensor API actually calls a different method that's been registered into the container, right? So we have that both calling kind of conventions where it can go call and do something, or we can call into the container. So cool. I think we got 30. Yeah. No, all right. Yeah. I'll start packing up.
So I might have missed the beginning, but how do you actually deal with like accessing a register, or let's say you need to access some custom I/O? How do you actually do that? Do you have to have a helper on the Zephyr side?
Yeah, so we have some marshalling code on our side that interfaces with the driver stack, and so we have to build and wire in all the sensors that we support. So we'd have to explicitly build support for that. We will have the ability to do custom for a customer or somebody using the project to actually build their own and then link that in themselves, right?
So will there be some kind of standard if you want to run that on 3 different platforms that you can have the same marshalling stack on all those platforms? Or I mean, at least at the top,
Zephyr solves
end.
a bunch of that for us because we can take advantage of the driver stack there, and then our marshalling code is largely the same. You'd have to write new marshalling code if you have a different type of device, right? So, but we have support for things like GPIOs, I2C, SPI. So we're going to build a lot of those, and then obviously there's no end to the number of peripherals that somebody can dream up. Sure. So some of those we'll have to we'll build it as part of the project, or somebody will have to build their own custom ones. So.
Okay, thanks.
You're welcome. Thank you. All right, appreciate it. Thank you. And then we're around, please contact, or we can chat in the hall.
Recording in progress.
Check.
This maybe. Okay. We still have 1 minute. Hi. Okay. I hope it's working. Can you hear me or not?
Yeah.
Seems to be working.
Yeah. I'm just going to turn it up a little bit. Do you mind if I put it in the middle?
Okay. Like here. Is this better?
Yeah.
Okay. So I guess we can start. So welcome everyone. I came here with kind of weird type of use case how to use this Zephyr. I'm teaching the operating system theory at the Technical University in Liberec. And my original background is in the hardware and the digital signal processing. And 20 years ago when I started to work in the industry, I was looking forward to write some pretty nice filters and stuff like this, but my first task was to write the operating system in assembler for some DSP chip. And I wish I would have known everything I know these days about the operating systems. So that's kind of logical that later on when I started teaching, my first subject were the operating system theory. So when I teach, I always try to learn my students, the important principles. And just to explain, I need to give you a little bit background related to the course and to the teaching, because I will later on explain you the work we are doing there in Zephyr. So our students who have the operating system theory as a subject at university, they are typically at the second year of their study, and they are not so experienced in, let's say, in programming in general, neither in the C or C++. And this is the main reason why we have decided not to use as a role model the Linux kernel, because it's too complex for them. And because our field of study is kind of general informatics, not just the embedded systems, they have very limited hardware knowledge. So we need to learn them this stuff as well. And we have two big groups of students in our classes typically. Some of them have, let's say, some general high school. They are excellent in math, but they do nothing about the hardware. And the second group, they are coming from, let's say, industry high schools focused to the electronics development. So typically they are stuck in math and theory, but they are excellent in hardware. So we need to learn them something together in the groups. The teaching at Czech universities, the most important part is that the teaching is divided into, let's say, two parts. We have some so-called theoretical talks, and they are for the whole year. It's roughly 100 of students, and then we have the practical labs. And the only mandatory part of the teaching are the practical labs, so you can imagine how many of them are coming to the theoretical lectures. But still, we can deal with that somehow. And we have roughly about 14 lessons per semester. So we need an operating system to play with, because we are explaining them a lot of theory, and I want them to use the real operating system and to learn how those principles are applied in some very real use case. So again, Linux is too complex for them. They are like those kitties, knowing nearly nothing. So you cannot phase them to work with the 6 million lines of code. So I was always looking for some real-time operating system, and since 2016 I was kind of happily using the Embed, mostly because it has the integrated environment which you can use from the browser, so there is no need to install any additional software to get all the demos working, and we had some STM32 based boards, and we had a lot of fun. With that, the problem is that Embed supports only the ARMs. The second problem is that all the examples and stuff we are using written by ST starts to be obsolete because they are not updating the examples there. And also they change the development environment. And also it was some new stuff was appearing on the scene. So that's why I have decided to move those labs to Zephyr. Mostly, from my point of view, what I really like here is that Zephyr supports several architectures, and in one lab you can say, we've explained you that you have several layers, let's say, in the operating system, and you need to be portable to different platforms. So within one lab, we are booting in the QEMU the x86 platform, and then we are booting some ARM-based board, changing just one configuration option to demonstrate that it's working. The other stuff, why I really like working in Zephyr is that you can emulate it in the QEMU, again, working with the real hardware. For especially our informatics students, it's sometimes kind of hard. What's also important that there is a lot of really nice, really perfectly described documentation and a big community of users, and plenty of libraries, and also some of my side intentions were to use the Linux are those device trees used in Zephyr, because later on in the 5th grade we have the embedded Linux courses, and we can build on what they have learned in the 2nd year. So these are the motivations why we have decided last year to switch from Embed to Zephyr. So next school year we will start completely with Zephyr, and now we are developing those labs. And because we have students coming from Erasmus to Czech Republic, and we have to do all the descriptions in English, so that's why I've decided to keep it open, let's say as an open source for everyone who is interested in those labs. So it's available on GitLab. It's still kind of under progress because the hard deadline is in September. The conference was just a soft deadline from that point of view. The general architecture is that in that GIP you will see there are plenty of folders, and there is some general README explaining the structure of the project, and each lab has its separate folder. Again, explaining what's, let's say, the topic of the lab. The plan is also till the September to convert the theoretical talks to have some more, let's say, theoretical background in those READMEs. So it shall come. The task was to create, let's say, 10 labs. Each of them shall be planned for roughly 90 minutes. We are switching, just now we are using, we are testing it on the QMO with the ARM, the M0 core and the RT core for demonstrating the user space, and the x86 cores to demonstrate that how far you can go with Zephyr, to how mature architectures you can use. And thanks to Hardvario sitting down there, we also have the Hardvario Chestel platform. And again, hopefully this will be the reference hardware we will use in the labs for our students. And the students from last year volunteered to do the beta testing to verify that everything is working properly for their younger colleagues. So we have a lot of work there. So this is the structure of, let's say, the theory. If you've studied the operating system theory, I guess that your course was exactly the same, because there is, from some point of view, if you want to start with the general theory, there is not so much to change, but still the content of those chapters is different and different year by year. But I want to just explain you what we are teaching, because when we discussed that, oh, you're using the Zephyr in teaching, so you definitely shall use, I don't know, some embedded stuff of programming like state machines or the idle modes or the interrupts, but this is not in our focus. We are focusing again to general principles, so we need to explain the features of the operating system in general. We need to provide to the students some hardware overview, because again, they hardly know that there is such kind of nice stuff like user mode or the kernel mode. We need to explain that we have microkernels and monolithic kernels and stuff like this. Then they learn about the processes, scheduling, memory management, and let's say till the end of the term. As you see, there is no networking, mostly because at our department we have guys who are much more experienced in networking than I am, so I keep it to their lessons mostly. And this is how the labs are related. So you will see in the Git, you will see those folders. So I try to explain how do I link it together. The problem is that at the beginning of training period, they know nothing. So if they do not understand the concept of the kernel, it's hard to do anything with the memory. So I will go deeper in those examples, trying to explain exactly what we are teaching this and what's the main focus on this lab. So, but you can see that the general structure. This is how it looks like in the GitLab. So again, the first one is pretty easy. You need to get it working on your computer. So this is the first lab. And there is, if you look to the sources, there is near nothing. Everything is in README. Download this part of software, download this part of software, and get it working somehow. So this works also on the Hardvario already. So we know that we can start in September, and it will probably work well. And as I measured it on my students, all this stuff is roughly for 60 to 90 minutes, depending on how fast they are downloading the stuff. The second lesson is dedicated to the configuration, because again, for young students, this is really absolutely confusing that you have many levels of entrance. There were many options, you did something, your software behaved somehow, then you changed something, you absolutely do not remember where it was, how you did get it working. They never seen, neither the key config, they never seen make mostly, they never used stuff like this, so we need to spend some time there. So again, no rocket science. I guess that they are just switching the board in this lab, so compile for this lab and then for that lab and do it from the command line and do it using CMake and do it using whatever you want to do. So at the end, they shall now all the proper ways of configuration the software, demonstrated on the real examples, because again, if you will read this in the Zephyr online documentation, you see the examples, but I've tried to do it in one lab in this 60 minutes to really test everything, to see the result, to see how it's working, not to provide just the general description. I missed the kernel. I see when I was working. So in the kernel lab, we are just demonstrating that, again, the kernel lab is mostly focused on the key config. We are demonstrating how you can configure the proper, how it's done, that you can port the operating system from one architecture to another one, and how it's different if you switch on the MMU, if you switch off the MMU, and stuff like this. And the last part of that lab is also the demonstration of some kernel API. The problem is that we are doing it before explaining devices, before explaining the threads, before explaining everything. So finally, I ended up with timers because this is the only stuff which is pretty easy. But again, to demonstrate how to include the sources and how to work with the operating system API, it's pretty nice. So they are writing some timers, just messaging, I'm the timers for time, this one and the other one. Then we go to threads. For the students, this is the first time in their life when they are spawning any thread anywhere. And I know from my colleagues who are teaching later on in later years that they need me to teach it properly, because in the higher applications in Java and in JavaScript and stuff like this, you need to be able to understand the thread concept. So we spend a lot of time there. They are spawning the threads. We are in these labs. We are demonstrating also the difference between the kernel space and user space, because it's nice to do it here. And we are playing a lot with priorities and explaining how to work. What does the stack mean, and what does all the other features of the threads are doing. So they are able to spawn a thread. So finally, we can go to the scheduling. This is, again, from, let's say, theoretical point of view. Zephyr is an excellent example, because you can just, in the key config, switch the scheduling. You can explain in the theory that there are several ways how to schedule the processes, and then you are going to key config, and like in the shopping center, you say, I want to have this, I want to have that, and let's just watch how it's behaving, how the tasks change the scheduling. So again, we are playing with those different the preemptive and non-preemptive scheduling, and explaining how it works, how your software is different, and stuff like this. So this is exactly the result of the soft deadline. So the work is done till the first lap in this part. And then again, the second most important part, which I am supposed to teach, are the mutexes, semaphores, and synchronization, because again, in the next years, they will need it quite often, and they need to understand the process. So for this, we have a lab which was really popular in Embed, because we had nice displays with full of colors, and the display serves as the parking lot. So you have 4 spots in your parking lot, and you spawn 10 threads, and those threads are cars. Each car has its unique color and different time of parking. So they are simulating in the real time how this is working, if they have a lot of cars at one spot, or if they are able to save the drivers' lives and stuff like this. So the only problem is that in Zephyr we have no displaying, so I need just to rethink the design of this lab to have the same fun as we had last. But I guess we will do it, because the parking lot, you need a lot of mutexes to synchronize about those shared data structures, and then there is that semaphore, and using this. They really understand how it's working. So this is the next part. And then we need to talk a lot about memory. Because again, if our students have some experience, they are mostly experienced in the application level programming, maybe JavaScript, maybe some Python. So we need to go in detail to explain at least the data structures used to reserve the memory, but also to explain that in Zephyr, you have no memory protection. You really need to think about it a lot. Again, I select what I like in Zephyr, that you can define your heaps, but you can use the CLabs as well. So later on, when our students go deeply in the Linux in their 5th grade, they are ready. We are building a path. Again, that's the second reason why I've selected Zephyr. It's that's so close to Linux from a lot of reasons. So you can also demonstrate it later on in parallel. Say, okay, you have learned this. It's simpler in Zephyr because it's for microcontrollers. And on a big servers, you can repeat what you have learned and it will stay similar, and you can reuse the principles. And also we need to explain the virtual memory because again, these days students have no clue how the memory is working. It's so low. If you are working in Python, it's so hidden, so they have absolutely no idea. So we need to spend some time here explaining stuff. And yeah, this is the last part, because again, we are playing a lot with the file system. So we are explaining how it's working. And then I have prepared some demo which emulates the SD card, and they using the APIs to access the file system and to understand it. So in the theory, we say them, okay, there is that FAT, but mostly you will see the ext and the BTRFS and whatever FS. And in the lab, we are going back to the FAT because it's simple, it's easy, and it's easily understandable. So again, you can't learn someone how to implement file system or how to work with that if you will start with the BTRFS, for example. But FAT is the old, nice FAT file subsystem is really great. And the last one, so I'm really fast, so at the end of semester, we will play also with the POSIX, again, because we want to teach them POSIX, teach them how to, what does it mean? What does it mean if you are POSIX compatible? What does it mean that everybody says if you are POSIX compatible, porting of the applications is easy? So there is a lab which kind of demonstrates this. And the last one is related to devices. Again, as I said, I really want them to explain them because they need to understand the driver structures. They need to understand the hardware description and how can we separate the hardware description from the code. So we are explaining them the elementary device tree stuff and the elementary drivers. So they are writing their own silly driver, doing something, and later on again, in 2 years, they will write their own modules for Linux kernel, and they will be somehow ready to do it. And that's all. So this is how we use it. The Git is available for everyone. I'm really happy for any comments. Again, this is not, our intention is not to learn them how to use Zephyr in their embedded application. We are using Zephyr because it's nice, cool, modern operating system. And we want to demonstrate this elementary stuff for our students to have a code which is understandable, where they can somehow orient and understand how it's working, which is definitely really complicated. In 90 minutes, you cannot explain how to write the driver for a Linux kernel, but you can do it for Zephyr. It's kind of easier. So that's all. I'm open to any questions, comments. Okay.
It's less a question, I think, and just more a celebration. But it's also true, and your students should probably know that those of us who sit here and work on Zephyr learned about OS theory from working on Zephyr 2, whether we admit it or not.
Yeah.
No, this is very cool. I love this.
Yeah, and generally speaking, I think that they show now that the operating systems are not just the iOS, Windows, and Linux, that the world is full of really nice systems. And I guess with a higher probability in their praxis, they will meet all the others. So I don't want to hide it from their eyes. Yeah. Okay. You can come. The public lectures are open for public in Czech. Everyone can come. Okay, so let's have coffee. Thank you very much.
Well, with that or DSP, Math, those are my two favorites. Right, it's like because there's so many. Well, so like I'm not actually. But I'm more like I actually like check out all the Right, so like if I want my USB interrupt to run. So like if you have a two drive and I see this all over. Okay. Oh, well, that's really interesting. I just figured I'd ask, specialize in work, you know, I was always fascinated by the halting problem. The halting problem that Turing said, you know, I saw one professor in the middle of the class. I went to Texas A&M. I said, wait a minute, so you're saying that there aren't enough computers in the universe to compute every problem? I was like, yes, that's exactly what I'm saying. Oh, cool. Well, then, yeah, I can solve all the problems. That's what I think. Yeah, exactly.
Hey, this is Ethan with E3 Webcasting. Are you the next speaker here? I'm not sure I know how to pronounce your name, but ANUJ. Oh, we're muted. There we go. Hey, are you the next presenter here? Just looking at the Zoom here. Wonder if we can get you set up to present.
Yeah, hi, we are going.
Yep.
Yeah,
Hey, there you are.
Yeah. And Naveen.
Hey there. Do you guys have slides you'll be sharing here? We're just going through configuring everything on the back end here. So if you're able to share slides as soon as you can, we'll get those queued up here. And then if you can also do a check on your audio, just to confirm that you can hear me and we can hear you.
Yeah.
Yeah.
Yep. Okay. Sounds a little quiet. Let me see if we can bring that up a little bit.
I'm sharing my slide.
Okay. Can you both give me another check or audio test here?
Works for
Hi.
me.
Can you hear me?
Okay, that's a little better. I'm just bringing up the volume just to make sure we've got enough volume in the room here. Slides are looking good. We're gonna get that configured.
Can you hear me?
Yes, we can hear you. Perfect. And so you guys are both able to see the room there, and we've got audio, we've got your slides, and then I assume you'll full screen that for the actual presentation.
Yeah, I can hear two voices. I mean,
Yeah, there is a
there are
delay
two.
also. Yeah.
Sorry, what was that? Could you repeat that? Sorry, had you said something? I'd missed what you said.
Yeah, there seems to be an echo after a few minutes. I mean, all the everything seems to be getting repeated after a lag of 1 minute. So whatever the
Okay, so there's an echo going on.
yeah, I just heard my sentence again.
Gotcha. We're looking into this.
Yep.
You don't happen to have the stream open, do you? Because if the stream is playing on your end, that will come through the YouTube stream, that is.
I need to be close. Oh yeah, I think you're right. The problem was because I had this open the window.
Gotcha. Okay. So the echo's gone then? We're good?
Yes, thank you.
Excellent. Still sounds like that's... Okay, we're just dialing in the volume over here. Naveen, could we get you to say a few words just so we can make sure our audio level is good?
Yeah. So I think you can hear me now.
Yeah, no, that's sounding good. Can you do a few more words? We're just dialing it in for this room here.
Okay. So this is Naveen testing test for audio, or
Cool.
I should speak more loud.
I mean, we're going to adjust it so it's comfortable for you. So I was just turning up the volume on our end to make sure it's good.
Okay. So I think audio test, audio test, audio test,
Okay, cool.
audio
I think
test.
we are good and think we're ready. So we're just going to put ourselves on mute and hang out for the next 7-8 minutes, and then we'll let you know when we're ready to go.
Yeah, sure.
Okay, we are at 4 o'clock, so we're ready for you all to jump right into it.
Yep. Okay. So I'll start. Thank you, everyone, for joining this session. In this today's session, we are going to take an overview uh, uh, about how to build the Jaifer applications with Yocto build system. So me and Anuj are going to present this session. So before start, my name is Naveen. I work as operating system developer at Intel. I'm the maintainer of Meta Jaifer and Meta Icon layers, and I actively contribute in BSP layers for Intel platforms. Anuj? I think Anuj should be joining. Right. So Anuj also work as an operating system developer at Intel, and he's my teammate. Uh, he's the maintainer of BSP layers for uh, BSP layer for Intel platforms. He's the maintainer of MetaDP, DK, MetaQuity, and couple of layers. And he also actively contribute in Yocto project development. So I think so we'll move to next. Okay, so in outline, we first at the beginning of this session, we will have a quick introduction about Yocto project. So not much in detail. Then we will go to a meta Jaifa layer and we'll see what are the features this layer provides. And then we will follow a step-by-step procedure to build Jaifa applications for QMU and how to run on these application QMU. And at the end of this session, we will have a use case in that we will build Jaifa as a virtual machine for Econ hypervisor. Okay. So Yocto project first. Yocto project is a very popular project, and it provides a set of tools that help us to create Linux-based images for embedded systems. It is supported by a very large active community that that make sure the Yocto project remains at the latest and stable releases of latest version of all tools and libraries that it maintain. Okay, so there are terminology we are not going to cover, so that will come throughout this session. So first is layers. So layers are basically the repositories that isolate the metadata, which is in form of configuration file or recipes. Uh, so it isolate in the from it could be based on the CPU architecture or it could be based on the functionality. So having a multiple layers help us to create a clean and build environment. So next is recipes. So recipes are the extension files with the .bb extension. So .bb represent here with big. So uh, so these files tells the build system from where to download the source for this particular piece of software, how to configure, compile, and deploy. Then comes bitbake. So bitbake is it in the heart of a build system. So that basically parse all the layers and recipes, create the task, schedule them for the execution. Okay, so next is Meta Jaifer. So Meta Jaifer, so we already know that Jaifer provides a build tool that we call West. So that does the repository management and which also provide a command line interface for compilation and deployment of the Jaifer application. So similarly, in parallel, Yocto project using MetaJyfer, Yocto project provides a way to build the Jyfer applications. So when we see the direct structure of this MetaJyfer, it have two internal layers. One is MetaJyfer core and BSP. Core have recipes to build the Jyfer kernel, and it have recipes for the applications that we want to build. It also Jyfer application recipes basically have the uh, the point of source from where it need to download the source applications that are part of the Jyfer repo. And the distribution is specific. So we have a configuration that we call distro configuration that have our project specific configuration. For example, MetaJyfer build with new lib C library. So that such configuration we keep in our distro configuration. Then comes MetaJyfer BSP layer. So that layer have board configuration. We call it machine configurations. So machine configurations have the architecture specific configuration that tell the build system for which architecture the images should be built. Okay, so we'll move next. Yeah. MetaJyfer already have support for a number of machine configuration, including ARM and x86 architecture boards. So then it also provide a UI interface for configuring the, to configure the Jyfer kernel using menu config. We have a demo also later part. By default, MetaJyfer build with the Yocto build tool chain, but Jyfer also provide a SDK. So MetaJyfer provide a provision to build either with the Jyfer SDK or by default Yocto toolchain. Then it have a QEMU support for the development purpose, and there are at the moment there are 3 tools supports are available for flashing: DFU, PyOCD, and BOSAC. So anyone who is using Jyfer should know about them. Okay. So now we are going to follow some steps to how to build the Jyfer applications for QEMU. So we are going to build a Hello World application, and at the end of this one, we'll try to run also that Jyper this Hello World application QEMU. So for that, first we need to do layer setup. Then there will be we need to do build configurations, and that if we want to enable some configuration for Jyfer kernel, that we will also do using menu config. Then we'll build it, and at the end we'll try to run on QEMU. Okay, so in the layer setup, we need to clone the Pokey repo. So Pokey is basically a reference distribution, and so it basically have the build system, contain build system, and all the metadata that is sufficient to get started to build or customize image. And the second, we need to clone MetaJyfer. MetaJyfer have some dependency on some Python libraries and tools. So these are coming from Meta Open Embedded Layer. So we need to clone that too. So once we clone it, so Pokey provides some script that does a build environment setup for us. So once we source it, it creates a build directory. So under build directory, there will be conf inside this one. There are 2 configuration files will be there, BB layers and local. So BB layers configuration in that, what are the layers we want to include in our build. So that should be listed there. So we can add either manually in BB layers, or we can use the bitbake layers command to do that. So in third one, so these are the bitbake commands. So that if you execute them, it will list what are the layers we want to include in our BB layers. So local conf have what are the configuration that is required for our application, or for so that kind of our user specific configuration we keep in local.conf. Okay, so in local.conf we need to set two variables. What is machine? Machine is basically we need to tell the build system for which machine configuration the image should be built. So we have for QMU, we have machine configuration, the file name qmu-x86.conf. So we need to define that. And the distro variable is we in MetaJyper provides a distro configuration. So the configuration name is Jyper. So we need to set it that way. Second is that is optional. If you want to build for as Jyper SDK toolchain, so we need to set this Jyper toolchain variant to Jyper. If you don't set it, by default it will build for with Yocto toolchain. The third is if for if for example for Intel there are number of Intel boards, and we have for all these boards we have a common machine configuration. So using machine configuration we can build for different boards. So there is a variable that called Jyper dashboard. If we set it for a particular board, then image will be built for that board. For example, here, if you want to build for Intel Elcart Lake, so we need to set. If you want to some other board like Upsquared or Alder Lake or Upper Lake, then we do the same for in Jyper board variable. Okay, so this is all the configuration we need to do. So once we do that, then we need to execute the bitbake command, and the recipe and the application name. So we call it the target image. So here our target image is our application name. So application name comes from the what is the recipe name for our application we created. So bitbake Jyper hello world. So once we execute, then on successful of this build, so the binaries will be created and deployed at the deploy directory under temp dir. So once this is created, now we can just run using, we can run this image in QMU using the run QMU command. We need to pass the machine name and it should run. So I have a demo here. So let me switch to that. So here first as local.conf. So we need to set the machine configuration to our QMU and the distro to our distro configuration Jyper. And have a look into bblayers.conf. So this is how the layer should be listed here. So this MetaOE and MetaPython comes from Open Embedded. So when this configuration is done, then we need to build the hello world image. So it will take a while. So I'll do fast forward. So it does do configure, compile, and deploy. Now build is successful. So now we can run in QMA using run QMA command. So here we can see is Java OS is 3.6.0 and this hello world for QMU x86. Okay, I'm going to stop here. Let's switch back to slide. Okay, so let's move to next. Yeah, so MetaJiver have a support for a UI interface for Java kernel configuration. So to do that with a bitbake and our application image name, and then -c and the menu config. So I have a demo too for that. So let me switch to back to that. Okay, so bitbake and our recipe name -c menu config. So in this example, we can see the board selection is QMU x86. And in this demo, I'm going to enable some debug configuration for Java kernel. Yeah, this is pretty much as doing menu config in Linux kernel. So once the configuration had changed, build system already know the configuration change. So it force the recompilation of the application. So it will throw the warning true. So now you can see here, it's throwing the menu config had changed. So recompile will be forced. So we can see when trying to build it again, it will force the compilation again. Yeah, we can see the do compile is in execution. So okay, so I'll stop it now here and we'll move back to slides. Okay. Yeah. So this sums up how how we can build Java applications, how we can configure the Java kernel, and how we can use the QEMU support for our development using the Yocto build system. Now, to take a real world use case, I'll switch a use case in that we will build Java as a virtual machine for hypervisor like Icon. So in this use case, so first, if someone is new to Icon hypervisor, so quick introduction is uh, Icon is a type 1 hypervisor that basically runs on bare metal hardware, and it in our use case, it build Java. It needs two VMs. One is a pre-launch VM that Java. We want to build Java as a pre-launch VM, and there is we want to build a custom Linux-based image as a service VM. So for that, we want to build. So what we want to do, we want to build both the images using a single build. So to do that, you have to provide a concept called multi-configuration. So in that, multi-configuration is a way we using a single command, we can build multiple images for different boards. Uh, Different boards. The boards, the images can be for different architectures. So to do that, we need to create manually a multi-configure, uh, multi-conf file, multi-conf directory under conf, and we need to create for our use case, we need to create two configuration files. One is for Jaifer and one is for service VM. So for example, here SOS is for service VM. So for Jaifer configuration, so we need to keep our configuration. So machine is, we are building for Jaifer for Acon board. So Jaifer board should be Acon and machine configuration set to Intel x86-64. And the distro is Jaifer. So this is the only configuration we need in Jaifer. And there is another variable. So local.conf configuration is common to for both the multi-conf files. So using BB multi-config variable, we are going to tell the build system it is a multi-config build, and you need to take care for what are the configurations we are. So what are for it need to build for different configurations. Okay. So SOS and Jaifer, these are the configuration names that we have created. And this is a configuration that is for required for to build a customized Linux image as a service VM. So to do that, actually it requires two more layers, that is meta-intel and meta-icon layer. So so this configuration, the machine configuration comes from meta-intel, and the distro icon board icon scenario that comes from meta-icon. These are icon specific configurations. So this is the necessary configuration. So at the end of this configuration, actually will make sure the Jaifer image, the Jaifer build is completed before the uh, service VM build is completed. So once the Jaifer image is created, it will install into the boot partition of the service VM. Okay, so now the configuration set, just using a single command, we can build both the images and also deploy the Jaifer in the service VM in the boot partition. So bitbake and MC is for multi-configuration. So and SOS is service configuration, and this icon image base is a service VM target image name. So once the build is successful, and in this example use case, I'm building for Tiger Lake. So once the image is ready, so flash it, boot it, then switch to Icon Yocto. Then once the Icon console is up, it should list both the because this Jaifer we are running as a safety VM, and this customized Linux image as service VM, so it should list both the VMs. So I have a demo, so I will switch to that. Okay, so icon is up, and now I am listing the VM list using. So we can see this both safety VM and service VM both are up and running, and icon cons allow us to log in and the two, so we can see whether they are both the VMs are actually running. So here you can see service VM is running, and now we will go back to icon console mode later. Now we will see the status of Jaifer VM. Yeah, so here we can see is our Jaifer is running, and we can see hello world icon and for 3.6.0 version. Okay, I'll stop it here and I'll go move back to slides. Okay, so that was the use case. So this is the end of the slide. So in that, if someone want to contribute in MetaJaifer layer, they can send patches to yocto-patches@list yocto.org mailing list. But the subject prefix for that patches should be with the MetaJaifer, and any issues found that can be reported at bugzilla.yocto.org. That was the last slide. And now, if you have any questions, please let us know.
Hi, thank you for your presentation. Is there a specific use case for using Yocto over the basic West build system? It seems like West is great for most cases. Was there a specific case that your team needed the Yocto build system to make yourselves more efficient?
Yeah, so that was first use case I just shown in my use case that we had a Yocto build environment for building the VMs for Acon. So we wanted to use the similar infrastructure to build the Jaifer also. So in that Meta Jaifer came handy. So that was actually this is the real case that it we use at Intel. And another is sometimes if someone want to use the latest build tools for testing Jaifer, for example, if you see the Jaifer currently it supports GCC 12, but Yocto have the latest have GCC 13. So it will be if someone want to test the latest build tools, it can be handy.
Okay, thank you. Any other questions? Check the chat real quick. And I do not see any questions in the chat just yet. So no, I think we're done with questions. Thanks.
Okay. So we can stop the session here.
Yes, thank you very much.
Thank you. Thank you. Thank you everyone for joining this.
I'm going to hand this back to you before I screw it up.